So good morning all of you. Is the audio and video fine? Good morning everyone. एक बार ऑडियो और वीडियो कंफर्म कीजिए. अनुषा, मिलन, स्वाति, सनत. So everyone just confirm the audio. एक बार ऑडियो कंफर्म कीजिए. Okay, it's clear. Fine then. So आज हम स्टार्ट करेंगे लेक्चर. सो बेसिकली लाइक इन दिस लेक्चर विल ऑल्सो इंट्रोड्यूस पंप्स बट द प्राइम फोकस इज टुवर्ड्स टर्बाइंस. ओके, सो टर्बाइंस के बारे में थोड़ा सा ध्यान से देखेंगे और उसके बाद पंप्स को भी थोड़ा सा इंट्रोडक्शन दे देंगे. ठीक है, सो विल जस्ट हैव ए व्यू ऑफ द लास्ट लेक्चर. सो लास्ट लेक्चर में हमने जो जो चीज़ डिस्कस किया था एक बार थोड़ा सा रिवाइज करेंगे. सो वी हैव सीन RTT ऑफ कोर्स. सो फॉर एनी क्वांटिटी V, for any quantity B, so the RTT Reynolds transport theorem, of course मैंने डेरिवेशन नहीं किया था लेकिन थोड़ा सा एक्सप्लेनेशन दिया इसके बारे में. so dB by dt of the system is equal to dou by dou t of integral over the control volume beta times dV plus over the complete control surface beta times rho VR bar dot n cap ds. So this is what we have seen because this is the mass flow rate, so mass flow rate times B dot, so which is cutting the cross section. So this is the RTT we have seen, and of course for B is equal to the linear momentum. Okay, so we have the linear momentum. We have seen the case of Euler's equation or basically the Newton's second law of motion in general. So in that Newton's second law of motion हमने कौन सा चीज डिस्कस किया था, like basically the impact of the jets, okay, on flat plates and how the momentum changes and all happens. So all these things हमने डिस्कस किया था. So basically system is given by some set of particles and the change in the control volume, of course by taking steady state. So इस टर्म को हमने जीरो किया था क्योंकि हमारे पास steady state का assumption है. So the rate of change of any quantity with time is going to be zero actually in that case. So this P is actually V, relative velocity, or basically this is the momentum, basically the relative momentum. So in that case we have got the equation, the net force acting sigma F on fluid is equal to m dot V relative summation at the outlet minus summation m dot V relative at the inlet. क्योंकि एट इनलेट हमने ऑब्जर्व किया था आउटवर्ड नॉर्मल एंड वेलोसिटी आर इन ऑपोजिट डायरेक्शन, सो एंगल 90 से ज्यादा है और जब cos थीटा हमने लिया था सो दिस माइनस साइन इज हियर. ओके, सो माइनस ऑफ समेशन m डॉट v एट द इनलेट. सिमिलरली व्हेन दिस b इज इक्वल टू एंगुलर मोमेंटम, so when this is angular momentum हमने एक इक्वेशन डेराइव किया. so sigma torque acting on fluid is equal to summation r cross m dot vr at outlet minus summation r cross m dot vr at the inlet of course. and इस वेक्टर इक्वेशन की वजह से हमने टेंजेंशियल डायरेक्शन में कैलकुलेट करने से we got power delivered by the fluid, power delivered by fluid to rotor. Normally if you have any rotating disc, so is equal to head. Of course this is per unit weight. Okay, so per unit weight. So when you calculate power per unit weight हमको length dimensions आया था. so we have h is equal to VW1 U1 minus VW2. basically 1 corresponds to inlet and 2 corresponds to outlet is what I have told you, divided by G. That's what we have here, correct? so this divided with G is what we got. Yes or no? so these are the things we have seen. And also this h from velocity triangles, we have also seen this h which is VW1 U1, basically subscript 1 is for inlet and 2 is for outlet. okay, so इसी subscripts इसी notation से हमने डेराइव किया था. so VW1 U1 minus VW2 U2 by G, and this implies h is equal to, So using this velocity triangles, मैंने एक छोटा सा चीज डेराइव किया था यहाँ 1/2g टाइम्स ऑफ v1 स्क्वायर माइनस v2 स्क्वायर प्लस u1 स्क्वायर माइनस u2 स्क्वायर प्लस vr2 स्क्वायर माइनस vr1 स्क्वायर. तो ये चीज हमने डेराइव किया था एक्चुअली. करेक्ट. सो दीज आर द थिंग्स दैट आई हैव शोन यू, एंड ऑल्सो यूजिंग Bernoulli's equation I have shown that this is, or basically if you multiply this 2g inside, by 2g and also by 2g, then this is due to change in static velocity head, change in velocity or static head, basically static head, and this is change in dynamic or pressure head, of course, change in dynamic or pressure head actually here. तो यहां तक हमने लास्ट क्लास में देखा था. इज दिस क्लियर टू ऑल ऑफ यू? एक बार टाइप कीजिए चैट बॉक्स में. कैन यू ऑल अंडरस्टैंड टिल दिस पॉइंट? यहां तक मैंने लास्ट क्लास में किया था. करेक्ट. वेलोसिटी ट्रायंगल्स लेके सिंपल मैथ्स, नथिंग मच. सो डॉट प्रोडक्ट ऑफ टू वेक्टर्स व्हिच gave us this simplification. Yes or no? Please type it in the chat box. यहां तक सबको समझ में आया या नहीं? अगर कुछ दिक्कत है तो बताइए. Everyone. Chat box काम नहीं कर रहे? Test कर. Okay, it's working, right? Fine. Is it clear to each and every one of you? Please type in the chat box till this point. Okay. Then, yeah, if it's clear, then let's move forward. Okay. So in this lecture, primarily हम ये चीज देखेंगे degree of reaction. So degree of reaction क्या होता है normally? Okay. So degree of reaction का definition पढ़ेंगे और dimensional analysis जो बहुत important part है turbines को modeling करने के लिए, क्योंकि फुल स्केल टर्बाइन्स बहुत ज्यादा साइज होता है. सो उसमें एक्सपेरिमेंट्स करना पड़ेगा, थोड़ा सा मुश्किल होता है क्योंकि लैब का स्पेस लिमिटेड होता है. सो वी डू डायमेंशनल एनालिसिस एंड वी डू मॉडलिंग ऑफ कोर्स. सो देन विल मेजरली सी पेल्टन व्हील, फ्रांसिस टर्बाइन, एंड इफ टाइम परमिट्स, आई एम नॉट श्योर, बट विल try to cover the Kaplan turbine as well, or else we'll look at the Kaplan turbine and the pumps in the next lecture. Of course, that's why I have kept a backup. Okay, so pumps के लिए 2 lecture मैंने schedule किया था क्योंकि I understood that if people if I have to revise the basics, then ultimately I should have some buffer. So इसलिए pumps के लिए मैंने 2 lectures डाला. ठीक है. So we'll start with degree of reaction. इससे पहले मैंने होमवर्क दिया था लास्ट क्लास में. किसी ने सॉल्व किया? So इस क्वेश्चन किसी ने सॉल्व किया था? मैंने पोल एक्टिवेट कर रहा हूँ. मान लो कि अगर आपने सॉल्व किया तो आंसर एंटर कीजिए. A tank shown in the figure has 2 nozzles at different depths as shown in the figure. If the net horizontal force acting on the tank is 0, the ratio of d1 by d2 is root k, value of k. Come on. अगर आपने सॉल्व किया तो आंसर एंटर कीजिए. 30 सेकंड्स दिया मैंने आंसर एंटर करने के लिए. Okay. Fine. So कितना आया आंसर? So चेक करेंगे. Look, let's see. A tank shown in the figure has 2 nozzles two nozzle exits at different depths as shown in the figure. If the net horizontal force on the tank is 0, the ratio of d1 by d2 is root k. पहले tank के ऊपर force क्यों लगाते हैं? When this fluid is coming in this direction, the reaction force of this fluid will try to push the tank right side. Correct? Similarly, जब fluid यहाँ से आते हैं उस टाइम पे इस टैंक के ऊपर लेफ्ट साइड रिएक्शन फोर्स होता है. करेक्ट? सो द टैंक विल ट्राई टू मूव द लेफ्ट, एंड इफ d1 and d2 are set properly, then ultimately what happens, the net force means the force due to this reaction and the force due to this reaction gets cancelled out and the tank remains stationary. Of course, okay, the net force acting on the tank is 0. So let's see how to do that. So let's calculate the velocity here is v1 and the velocity here is v2, of course. Okay, so let's take a control volume which includes the tank, because the force on the tank is what we are interested. So let's take the control volume to be this tank, of course. Okay, So when the control volume is tank, K is 2. Okay, I don't know, let us check. So if I think 2 is correct answer maybe. Okay, so let's see, this is V1 and that's V2 of course. Then if you apply this thing, sigma F on tank is equal to minus sigma F, of course in the x direction because it's a horizontal, both the things are in horizontal direction. So sigma Fx on tank is sigma Fx on fluid is given as 0. Okay, so ये चीज पता है हमको. So net force acting on the tank is 0. So if net force acting on the tank is 0, then since fluid and tank are in contact with each other, net force acting on the fluid should also be 0 actually. Okay, so this implies what is the net force acting on the fluid actually? Let's see. So the fluid, this is equal to the momentum change summation m dot v out in the x direction minus summation m dot v inlet in the x direction is equal to 0. Now tell me something, for this control volume, at any point on the control surface, is there any fluid inlet? At any point on this control surface, is there any point where fluid is cutting and going inside? Come on, type it in the chat box. Let's say this is the x direction normally. So at any point, is there a point on this control surface where fluid cut the control surface and go inside the control volume? Come on, type it in the chat box. No, correct? There is no point where fluid is actually cutting the control surface and going inside. Okay, so therefore this V inlet terms is 0. There is no location where fluid is going inside. Correct? No inlet. So this implies summation at outlets has to be 0. So let's say the mass flow rate to this is m dot 1 for the time being, and the mass flow rate to this is m dot 2 of course. Then if you write this equation, this implies first you have two outlets. This is first outlet and this is the second outlet of course. So m dot 1 into, now velocity at this outlet is v1, लेकिन इस v1 negative x direction की तरफ है, correct? So if you want to put v1, then this v1 should be plus or minus. Come on, type it in the chat box. This velocity is coming towards the negative x axis, we know. So this, and tank is stationary, so relative velocity is also v1. Then this v1 should be positive or negative. Come on, type it in the chat box. Fast, a bit faster. v1, should I put positive or negative? Negative, correct? So minus v1 plus, again at the second outlet, m dot 2 times v2. Now v2 is actually in the positive direction. Since tank is stationary, the relative velocity is also positive. So m dot 2 v2 is equal to 0 of course. So this implies, what is m dot 1? मान लो कि यहाँ diameter d1 दिया था. So m dot is equal to, so since velocity is exactly perpendicular to the area of cross section, you can use rho m dot 1 is a1 v1, and here m dot 2 is rho a2 v2 actually here. Okay, so this implies minus m dot 1 rho a1 v1 into v1, so v1 square plus rho a2 v2 square is equal to 0 actually here. So density and density can be cancelled because it's common in both the cases, and area is pi by 4 d square. So this equation finally हमको ये देते हैं, d2 square v2 square is equal to d1 square v1 square actually here. Okay, and हमको d1 by d2 का value चाहिए. So therefore d1 by d2 whole square is equal to, so d1 by d2 whole square is equal to v2 by v1 whole square, v2 by v1 whole square actually here. Okay, so this is the value. Now let's see, but d1 by d2 is actually okay, so we need to calculate what is v2 by v1. So v2 by v1 हमको कैसे पता चलेगा? Bernoulli equation apply करेंगे. So you know, if you apply Bernoulli equation, this tank is open to atmosphere, it's a free surface. This tells you that it's a free surface actually here. Okay, so if this is free surface, then if you apply Bernoulli equation between this point, say for example A, and this point at the exit B, so A point B, okay, or A point C. Now if you apply Bernoulli equation between point A and point B, look what happens. Applying Bernoulli's equation, first between A and B, assuming no loss when the fluid is sliding all over. Okay, so it's a smooth flow. Then in such case, if you apply Bernoulli's equation between A and B, we can get PA by OA G plus VA square by 2Z plus ZA is equal to, assuming no loss, nothing, PB by OBG plus VB square by 2G plus ZB, of course. Okay, so this is the Bernoulli's equation you can apply. Now, points A and B. A is open to atmosphere, B is also open to atmosphere, correct? B to this exit, whatever the fluid is coming, that's also going to this atmosphere actually. Okay, so at A and B, if you check, then this PA and PB is same, और जो fluid होता है वो liquid, so it's not compressible and all, so we are not taking any compressible flows and all, it's purely incompressible, so these two terms gets cancelled up. Okay, then what's the difference between these two? ZA minus ZB is H. Okay, so if you bring this term this side, so this can be written as H, of course, if you make this 0. Then VA square and VB square. So first of all, it's a large tank. Tank का dimension नहीं दिया था, so हम assumption करेंगे कि बहुत large tank है. So if this is a large tank, if two exits are coming out, the velocity at which this fluid level comes down is very slow. Correct? Yes or no? Please type in the chat box. Can you understand? So if these are two exits and if this is a large tank, then the velocity at which this free surface comes down will be very, very slow. Like मान लो कि आपके घर पे एक filter है, okay? So and if you are filling the bottle, then the water level in the filters comes down very slowly. Correct? Have you seen that? Normally this fluid velocity will be like 5 meters per second or some 6 meters per second, but the level of that filter water level in the filter coming down will be like almost some 2 mm per second or 1 mm per second of that range. Okay, so that is very slow, it's almost like some hundreds of times lesser. So इसकी वजह से हम इस VA को, or basically rather than telling this VA square, since VA is very, very less than VB, this implies VB square minus VA square by 2G is approximated as VB square by 2G actually here. Correct? So this is VB square by 2G actually here. Okay, so this is VB square by 2G. So what we can do, we can neglect this term. Neglecting this term, okay, as compared to this. So इससे हमको पता चलेगा VB value, VB square is equal to 2GH. That's it. Okay, from this equation VB square is equal to 2GH, as all terms are cancelled. So what is VB actually? VB is nothing but V1. So therefore V1 square is equal to 2GH, of course. Okay, so this is V1 square is equal to 2GH. Similarly, if we apply Bernoulli's equation between A and C, this will give you V2 square is equal to 2G into, so height difference क्या है from 2 and to A, so this is 2H, so 2G times of 2H actually. Okay, because if height difference between A and B is H, you got V1 square is 2GH. Similarly, if height difference between A and C is 2H, you will get V2 square is equal to 2G 2H actually. Okay, so if you calculate this, then what happens? Let's see. Oh, sorry. So then this is equal to, therefore D1 square or D1 by D2 whole square is equal to V2 by V1 square, which is V2 square by V1 square. Okay, so let's see, D1 by D2 whole square is equal to, what is V2 square? This guy, 2G into 2H. Okay, so this is 2G 2H by, this is 2G times H. So if you simplify, 2G cancel होता है, H, so D1 by D2 is equal to square root of 2 actually here. Okay, so square root of 2 is the correct answer. So यहाँ जो root के अंदर value है वो हमारा k का value, so this is k, of course. So therefore k is equal to 2. That's it. It's not a tough question, very easy question. So what if he would have given to consider the velocity VA? Then we'll put VA in this part and we'll do the calculation accordingly. That's it. Okay, because they should give what is the velocity the fluid is, either they should give the V1 or we should give VA, only then we can calculate. Okay, but normally from the physics we can understand that VA is very, very small, it can be neglected. Okay, like बहुत सारी जगह पे हम ऐसा कहते हैं, normally in Rankine cycle and all pump work neglect कर सकते हैं, correct? Because you know the control volume work is minus integral VdP, and जो pumps होते हैं, pumps liquid handle करते हैं, so this V is very small. So compared to the turbine outputs, all these things, boiler input and all the enthalpies, the enthalpy difference across the pump is very very small. इसकी वजह से सारे पावर प्लांट्स या सारी जगह पे रिफाइनरीज हर जगह पे अगर पंप को चला करना है तो we'll directly take power from the electricity and we'll supply. Okay, but you can never see compressor running with electricity, then it's a complete loss. Okay, so normally अगर plant में compressor है तो एक turbine हम install करेंगे. ठीक है. So this is what we have. So d1 by d2 is square root of 2. It's a बहुत simple question है लेकिन थोड़ा सा concepts की ज़रूरत भी है इसमें. Okay, so momentum equation and then after bit of Bernoulli equation to solve. That's all. Okay, so 2 is the correct answer. देखेंगे कितने लोग आंसर करते हैं. 2 50%. Okay, Alok Milan. Yes, good. Okay, so 2 is the correct answer in this case. So मैंने और एक क्वेश्चन भी दिया था. इस क्वेश्चन किसी ने सॉल्व किया? A simple turbo machine is constructed from a disc with two internal ducts that exit tangentially through square holes. Okay, so यहाँ जो hole है, this is square hole. I think you can see this diagram clearly. Okay, I hope you can see this diagram. So there are two square holes as shown in the figure. Water enters normally to the disc, means water is entering normal to the disc, and this disc is rotating at to a small center. The disc must dive at 250 rpm. So the speed of the disc should be 250 rpm. So ये तो start ही नहीं हुआ. Okay, I'll start this. A small device whose retarding torque is 1.5 Newton per meter. The proper mass flow rate of the water to the disc is dash kg per second, round off to 2 decimal place. कितने लोग पहले सॉल्व करने की कोशिश किया था? आंसर आया या नहीं वो दूसरा बात है, लेकिन कितने लोग कोशिश किया सॉल्व करने का? मैंने इस क्वेश्चन होमवर्क पे डाला क्योंकि बहुत सारे लोग ने एक्सी एग्जाम लिखने का सोचा है. सो आई पुट दिस क्वेश्चन क्योंकि ऐसे क्वेश्चंस एक्सी में आया था. ओके, 2021 में आया, 2 में आया. ओके, देयर आर लॉट ऑफ थिंग्स. कितने लोग अटेम्प्ट किया? नहीं हुआ सर. ठीक है, कोई दिक्कत नहीं, लेकिन कोशिश की थी पर पेन ही नहीं चला. ठीक है, कोई दिक्कत नहीं. अब देखेंगे कैसे सॉल्व करेंगे. एक्चुअली मैंने इस क्वेश्चन ट्राई किया था, नहीं हुआ. ठीक है, कोई दिक्कत नहीं. इस क्वेश्चन एक्चुअली फ्रैंक एम वाइट से लिया था मैंने. इस क्वेश्चन की एक स्पेशलिटी है कि फ्रैंक एम वाइट में इस क्वेश्चन का आंसर गलती दिया. ओके, सो नॉर्मली जब पहली बार मतलब 5 या 6 साल पहले मैंने इस क्वेश्चन को पहली बार देखा था उस टाइम पे. सो जब मैंने सॉल्व करने की कोशिश किया था उस टाइम पे आंसर्स मैच नहीं हुए. ओके, सो लेकिन उस टाइम तक मुझे आंसर से ये सब चीज़ आता है. सो आई वॉज लाइक सिमुलेटिंग दिस एग्जाम्पल and exactly all the simulators are giving the same answer what I got. So थोड़ा सा मुश्किल से फ्रैंक एम वाइट की सॉल्यूशन मिला था इस क्वेश्चन का. उसमें से एक कैलकुलेशन मिस्टेक किया उन लोगों ने. सो इसकी वजह से आंसर डिफरेंट हुआ था. ओके, सो इस क्वेश्चन का एक्चुअल आंसर क्या होगा हम देखेंगे. ठीक है, सो लेट्स सी. पहले एक चीज पता है सबको, फ्लूइड इज कमिंग आउट इन दिस डायरेक्शन एंड ऑल्सो इन दिस एग्जिट इट्स मूविंग इन दिस डायरेक्शन. ओके, सो इन दिस डायरेक्शन. सो कैन यू टेल मी, अगर एक 2 टैंजेंशियल जेट्स इस डायरेक्शन से आ रहे तो इस डिस्क कौन सा डायरेक्शन पे रोटेट होगा, एंटी क्लॉकवाइज और क्लॉकवाइज? ये चीज बता दीजिए. When these two fluids are coming out like this, then this disc will rotate in which direction, anti-clockwise or clockwise? Come on, type it in the chat box. Anti-clockwise? Pakka? How many of you say clockwise? एक ही बंदा भी नहीं है. हाँ, पंकज. Anti-clockwise? Anti-clockwise? Good. So this disc will actually rotate clockwise. This disc will rotate clockwise actually. क्यों? पता है किसी को क्यों clockwise rotate होते हैं? Because when this fluid is trying to see, आप सबको पता है एक टैंक है. ओके, सो इस टैंक को यहां एक होल बनाया हमने, इसमें पानी है. सो फ्लूइड इज कमिंग इन दिस डायरेक्शन. टैंक will move right or left? Please tell me. In this simple case, if you have this fluid and if there is an exit, when this is moving in this direction, then this tank will try to move which direction? Along with the fluid or opposite to the fluid? In which direction this tank will try to move? Right side or left side? फ्लूइड मैकेनिक्स को बहुत कॉम्प्लिकेट कर रहे हैं हम, है ना. आराम से आसान से होता है चीज़, हमने इतना कॉम्प्लिकेट कर रहा है क्यों? गेट का स्टैंडर्ड यही है, ओके, ऑपोजिट डायरेक्शन, करेक्ट। सो सिमिलरली जब फ्लूइड इस एग्जिट से बाहर आता है उस टाइम पे इस डिस्क के ऊपर रिएक्शन फोर्स जो होता है, सो दिस इज द रिएक्शन फोर्स। सिमिलरली ये भी रिएक्शन है, सिमिलरली ये भी रिएक्शन है। सो नाउ the reaction torques or the reaction forces acting on the disk are in this direction, and the torque which is generated, because obviously this is the radius, so you know you have some radius of the disk, capital R. Then in this case, if this is the reaction and R, the couple generated by these two reaction forces will drive the disk clockwise. Okay, is this clear? So that's what you have. So basically the reaction forces will rotate this disk in the clockwise direction actually here, like this. So this is clockwise. So yahan tak sabko clear hai ya nahi? So when fluid is trying to come out with a velocity v, this point or this disk will actually try to move in this direction tangentially, because at every point it has the fail velocity. So which is, let's say if this disk is rotating at an angular velocity omega, so and if this radius is r, capital R, so capital R omega would be the velocity of this point. Okay, means मान लो कि इस exit से fluid v velocity से बाहर आने की कोशिश कर रहे हैं, then this point on the disk, means basically this disk here will try to rotate in the anti-clockwise direction. This disk will try to move back in the r omega direction actually. Okay, so this is what we have. Now let us apply the angular momentum principle. बहुत आसानी चीज है. Let's see. Net torque. So net torque acting on fluid in tangential direction just for rotation and all. So net torque acting on the fluid is equal to summation m dot vr, because I've told you जब tangential direction में हम apply कर सकते हैं r cos momentum and radius are always perpendicular to each other. Tangential component of velocity and radius are perpendicular to each other. So sin, normally मैंने last class में explanation भी दिया था, normally आपके पास ये है, okay, at inlet और outlet, but लेकिन जब tangential direction में आप resolve कर सकते हैं उस टाइम पे इस component is r in the radial direction and this is in the tangential direction. Angle between radius and tangent is 90. So this tangential component is just equal to product of these things, correct? This v in the mv in the tangential direction. Okay, so that's why I've told. So m dot vr is what you have. Of course dot is also there because per unit time is what we are doing. So now if you see these things, we have at on fluid, so at outlet minus summation m dot vr at m dot vr, this product at the inlet actually. Okay, so if you write on disk instead of fluid, if you write disk here, net torque acting on the disk is equal to, यहाँ माइनस आएगा और ये भी प्लस हो जाएगा बस. ओके, बिकॉज यू मल्टीप्लाई विथ ए माइनस साइन, इनलेट माइनस आउटलेट. ओके, नाउ net force acting on the disk. Okay, so net force acting on the disk is this. Now tell me one thing, let's read the question. A simple turbo machine is constructed from a disk with two internal ducts that exit tangentially through square holes. यहाँ जो क्रॉस सेक्शन है वो square hole, so fluid is coming through this square hole. So this is 2 centimeters and this is also 2 centimeters. Okay, now water enters normally, matlab water is entering normally at the center and it is getting splitted. The disk must drive at 250 rpm. Okay, so what is the speed of the disk? N is equal to 250 rpm. So omega कितना होगा? 2 pi n by 60. So 2 into pi into 250 by 60 and इसका वैल्यू कितना होगा? So 0 0 2 3, so 25 pi by 3 radians per second. ये होगा angular velocity of the disk. Okay, normal angular velocity of the disk. Then it is connected to a small device whose retarding torque is 1.5 Newton per meter. So the torque that's acting on this is 1.5 Newton per meter actually here. Now tell me something here. The torque with which it should rotate the other device is 1.5 Newton meter. If the torque transmitted is 1.5, assuming no loss, then the torque acting on the disk should also be 1.5, correct? Because gears and all are used for the transmission, shafts and all are used for just transmission. So if the if the torque which is to be transmitted by the disk is 1.5 Newton by meter, if there is no loss in the shaft or something, the disk should also rotate at, the disk should also be subjected to 1.5 Newton meter torque actually. Okay, so let's see torque acting on the disk. Okay, so torque acting on the disk is this, whose retarding torque is 1.5 Newton meter. The proper mass flow rate of the water to the disk is dash kg per second. So what we can do, first of all, at inlet, do you have any inlet actually? So if you check, the fluid is going at inlet only at the center. Okay, so through normally. At this point, if this is the disk, at this inlet point, the fluid has mass flow. Of course, there is some mass which is entering. So ultimately, if there is mass flow, there is velocity. But what is the radius at this inlet point? Can someone tell me? What is the radius at this inlet point? The fluid is entering normally at this point and then getting split up. So at the entry to the control volume, if you take this disk as the control volume, at the entry point, what is the radius you have? At the fluid inlet, the point where the fluid is cutting the control surface and going inside, उस जगह पे radius कितना है? The fluid is entering to the center of the disk, correct? So what is the radius at this point? 0, correct? And this is the only point where fluid is going in. So ultimately, ये होगा 0. So this radius at the inlet is 0. So इसकी वजह से यह पूरा term 0 हो जाएगा. Correct? Now we have only one thing. So net torque acting on the disk. So let's take modulus on both sides because the reaction torque and these things can happen. So we take the modulus. So because of this, what happens? 1.5 is equal to 1.5 Newton meter is the torque, net torque which is in interaction. Then summation m dot Vr at the outlet. So how many outlets are there? There are 2 outlets. Okay. So outlet 1 and also outlet 2 actually here. Okay, so we have 2 outlets, outlet 1 and outlet 2. And एक चीज बहुत समझ में आता है कि दोनों आउटलेट सिमेट्रिक है, मतलब यहाँ जो चीज होता है यहाँ भी सेम चीज होता है, करेक्ट? सो नाउ लेट्स सी 1.5 is equal to summation, so 2 outlets which is m dot Vr at location 1 plus m dot Vr at location 2. And you know this is relative velocity Vr basically. I've been telling all the times this velocity which you have is relative, so Vr and Vr of course, correct, in general, because here the disk is not stationary, it's moving, so we have to take a relative velocity obviously. Then let's see at 1 and 2 situations are similar. Okay, so this implies 1.5 is equal to m dot. So let's say if the total discharge is q. Okay, they're asking about m dot in kgs per second. Okay, so total discharge is m dot, then through 1 m dot at section 1 is going to be m dot by 2 actually here, correct? M dot at section 1 is going to be half of the total mass flow, so it is m dot by 2. V dot r. So what is V dot r? Can someone tell me? At this point exit, the fluid is trying to come out in this direction and this disk is trying to move back in the reverse direction. So if 2 velocities are in opposite direction, the relative velocity should be v plus r omega or v minus r omega. Tell me, it should be plus or minus, plus of these 2 or minus of v minus r omega. Tell me, we should use plus or minus. This is an important point here. Come on, type in the chat box. It should be v, the relative velocity. Fluid is trying to come out in this direction and this jet is, this disk is moving back in the direction. So what is the relative velocity? V plus r omega or v minus r omega? Minus, plus, something? नेगेटिव, माइनस, करेक्ट. ओके, सो नॉर्मली यहाँ एक मिसकन्फ्यूजन है, बहुत सारे लोग यहाँ v प्लस आर ओमेगा सब्स्टिट्यूट करते हैं. ओके, दिक्कत ये होता है कि यू कैन ऐड ओनली इफ द बॉडीज आर नॉट इन कॉन्टैक्ट. ओके, सो मान लो कि 2 डिफरेंट बॉडीज है जो कॉन्टैक्ट पे नहीं है, ठीक है? सो then when they are trying to move in opposite directions, we'll add the velocities. Okay, like obviously, you know, if there is a 2 cars which are starting and if they are moving towards each other, the time at which they meet actually is divided by the relative velocity, which is sum. But when bodies are in contact and if they are moving in the opposite direction, then the relative velocity is negative. मान लो कि मैं एक escalator के ऊपर हूँ, ठीक है? So when escalator is moving up in the upward direction, if I am also walking in the same direction, the time in which I reach the top will be very less, correct? क्यों? the relative velocity is my velocity plus this escalator velocity, correct? So this escalator plus me both will move in the same direction and we are in contact. So ultimately my relative speed बढ़ेगा, okay? And when the substances are in contact with each other and if they are moving in the opposite direction, so मान लो कि accelerator ऊपर जाए और मैं नीचे जा रहा हूँ, okay? उस time पे क्या होगा? Then the relative velocity becomes minus, okay? The time it takes to move up will be very small. So since these two are in contact with each other, the relative velocity at this point is v minus r omega actually, okay? So v minus r omega, r times omega into, then what is the radius at which it is leaving? So this is the center of rotation, then this distance, this radius is r, so this is r. And similarly at the second outlet also the same thing happens, so into 2 is what I'm writing, because this is at the first outlet plus at the second outlet also you'll get the same quantity, so that's why I'm multiplying 2 of course, okay? So this 2 and 2 cancels up. Are you all getting the things? Are you all understanding step by step? Yes or no? I have written only 3 steps till now and this second step is known to anyone, so I'm writing only 2 steps, but in these 2 steps there are a lot of concepts which are involved. Why r is 0, why inlet is 0, okay? At outlet what we are doing, all these things has to be taken a little care, okay? Then let's see what is this v in this case. Omega हमको पता चला, so this is like 25 pi by 3, but what is v? So v is nothing but the velocity at which fluid is coming, normally by continuity we can answer, so which is like m dot by rho area. So area is what we have, okay? So because m dot equal to OAV, so v equal to m dot by rho A. So at each section m dot, okay, v1, let's say you call this to be 1 for example, okay, to avoid the confusion, so m dot 1, so v1 is equal to, now what is m dot 1? M dot 1 is half of the mass flow rate, correct? And rho A, so we can write this as m dot by 2 rho A, so v1 is equal to m dot upon 2 rho area of the duct, which is like 2 centimeters and 2 centimeters, okay? मद क्यों किए है sir? What is mud actually? Didn't get you. MARD matlab? Okay, please explain. Meanwhile, I'll finish this calculation. So this is like 2 rho A is what we can write it. Okay, so let's see. This is V1. So let us substitute here. So substitute करके simplify करेंगे और देखेंगे आंसर क्या आएगा. So this implies 1.5 is equal to m dot into V1. So V1 is m dot by 2 rho A minus r omega. So r can be written as d by 2 omega into r, one more r, so which is d by 2. So this is a quadratic equation in m dot. We can solve. Okay, modulus, because it's like the retarding torque on the disk, so torque acting on the disk by the fluid is like minus. That's it. Okay, nothing other than that. It's like work done on the disk, so it's negative. That's all. Okay, just to take the compare the values, I have taken a modulus. Nothing big deal. Normally it's like minus 1.5 because it's like the work done on the disk. Okay, that's it. And that would be negative obviously because work is added to the disk like this. Okay, sorry. So let's see in this case. So this is d by 2 of course. So m dot by 2, it's a quadratic equation you can solve. So if you solve this equation, then let's calculate what's happening here. 1.5 is equal to m dot into m dot square by 2 into its water, so density is 1000, area, so area kitna hoga? This is like a 2 centimeter by 2 centimeter duct, small duct, so area is 4 into 10 power minus 4, correct? So this value minus m dot into d by 2 omega, so m dot times d by 2 omega. So what is d? Diameter. The diameter of this disk is like 32 centimeters. Okay, so diameter is 32 centimeters. They have given this is like 32 centimeters. So diameter is 32 centimeters. So m dot into 32 into 10 power minus 2 by 2 into omega. So what is omega? 25 pi by 3. So this complete value into d by 2. So that d by 2 I am bringing it here. So 2 by d is what I can write. So 2 by this d diameter is 32 centimeters. So 32 into 10 to the power minus 2. So this is the equation. In this equation, a key unknown plus, where it's plus, I didn't get you. It's correct, right? So basically you can check 1.5 is equal to this term, so this is what you have. I'm just substituting the values. It's a quadratic equation, you can solve ultimately. So we have to be little careful with the substitutions. So this is like 1 by 0.8, so 0.8 here, and this is something like 25 and 32. So 32 into 25, we can write it as 8, and these two cancels up. So this is 4, so 4 pi by 3. So we'll see something like 1 by 0.8 m dot square minus 4 pi by 3 m dot minus, now let's substitute this is like 300 by 32, so 300 by 32 is equal to 0. This is the quadratic equation which you can solve, of course. Okay, you can get the value of m dot. So let's see what is the value of m dot in this case. Kgs per second. So m dot is some kgs per second. So if you simplify this, let's take a quadratic. I can apply minus b plus or minus all these things, but I'll use a solver directly. Okay, so quadratic solver, quadratic equation solver. Oh, fine. Okay, so let us use this quadratic equation solver. Good. So we got the solver actually here. So let's solve ax square plus bx plus c. So what is the value of a actually? 1 by 0.8. So 1 by 0.8. Okay, so normally you can get the Casio and you can calculate this, but let's use a solver anyway. So b is minus 4 pi by 3 minus 4 pi by 3 actually, minus 4 pi by 3. Okay, and what about c? C is something like 300 by 32 minus 300 by 32 minus 300 by 32 actually here. I hope you can see this. Okay, so I'm just solving a quadratic equation, that's all. Okay, then you can check it up, the values of x and all we got. Oh, it is some different coefficients has taken, right? 1 0 minus 300. Let's change it. Let's calculate quickly. 1 by 0.8, how much it is? 1.25. Okay, so this is 1.25 because the calc is not taking directly, so this is like 1.25 minus 4 pi by 3, 4 pi by 3, so minus 4.1887. So this is like 4.1887. And what about 300 by 32? Almost 9 point something, 9.375. We got the values, so let's substitute and calculate now. 1.25, and this is something like minus 4.1887, 4.1887, and this is like how much it is? Minus 9.375, minus 9.375. Okay, so we can calculate now. So if you calculate, we got the values to be, these are the x values, 4.886, 4.88659 kgs per second, and the other value is negative, but negative thing is mathematically it's out, but physically mass flow cannot be negative. So 4.886 kgs per second is the actual mass flow rate in this. Okay, you see this question has solved in almost some 4 steps. Of course it is slightly calculation hectic because of all these terms involvement, because I thought of deriving a general formula. Okay, so that's why I got it here. But in this step is like simple conversion, this step is also like simple conversion. So first step, second step and third step, that's all, and maybe fourth step for little calculation of quadratic equation. That's it. ये क्वेश्चन मुश्किल नहीं है, लेकिन कॉन्सेप्ट्स की क्लैरिटी थोड़ा सा होना चाहिए बस. Okay, is this clear to all of you? Yes or no? Please type it in the chat box. Did you all understand? So 4.88 is the correct answer in this case. I think in the Frank and White some other answer was given, but actually 4.88 is the actual answer for this question. Okay, you see once you are up to this point, there is nothing complicated. Once you get this equation, मान लो कि अगर एक बार इस equation आपको मिला था, so then it's just a bit of maths calculation is what you have to do. But this is that equation. That's it. Okay, so 4.88 is what the mass flow rate, total mass flow rate, which has to go into the turbine to rotate, okay, to supply a torque of 1.5 Newton meter. Got it? So it's a nice question, actually beautiful question. The other question जो मैंने दिया था 3 arms with the sprinkler, वो DPP में ऑलरेडी आपको सॉल्यूशन मिल गया, ठीक है, तो उसमें कुछ दिक्कत नहीं है. उस क्वेश्चन भी मैंने फ्रैंक एंड वाइट से लिया था, बिकॉज फ्रैंक एंड वाइट एक अच्छा सा बहुत अच्छा बुक है जिससे गेट में डायरेक्ट क्वेश्चन आते हैं काफ़ी बार. ओके, तो लेट्स मूव ऑन टू द नेक्स्ट टॉपिक्स ऑफ कोर्स. सो डिग्री ऑफ रिएक्शन. ओके, सो यहाँ तक सबको क्लियर है या नहीं? अगर इफ यू हैव एनी इश्यूज और डाउट्स प्लीज आस्क मी. डीबीपी आया नहीं है? आया था ना, ऑलरेडी अपलोड हुआ. ठीक है, दोबारा चेक कीजिए, अगर नहीं हुआ तो कुछ बैचेस में, बैच का नाम टेलीग्राम ग्रुप में मेंशन कीजिए, मैं बैक एंड टीम से बात करता हूँ. फाइन. सो लेट्स सी डिग्री ऑफ रिएक्शन. ये बहुत इंपॉर्टेंट चीज़ है, गेट में काफ़ी क्वेश्चंस आया था, मतलब टिल गेट 2022 एंड ऑल. सो लेट्स सी व्हाट इज डिग्री ऑफ रिएक्शन. डिग्री ऑफ रिएक्शन in a turbine, in a turbo machine, normally is denoted with capital R. So degree of reaction R is given by, R is equal to change in pressure head by change in total head. Change in total head of a turbo machine. Change in total head of a turbo machine. Like for example, if you see, मैंने last class में भी बताया, if you have a turbo machine, for example, this is general. Again, I didn't start turbines. Okay, this is all the analysis of Reynolds transport theorem, Euler's equation, degree of reaction. These definitions are for any turbo machine, pump, compressor, turbine, anything. Okay, so if this is a turbo machine, then you know, if the total head available is H1, the total head available that's going out is H2, then head supplied to the turbine or head change across the turbine to the turbo machine is actually H2 minus H1, which you have, or H1 minus H2, because supplied is what we are telling. So H1 minus H2, this is what you have. Okay, so this head what is supplied to the turbo machine, normally if in the case of a turbine, for example, if this is head supplied, then that head is the difference between the total energies, which I have shown you. Okay, now this total head supplied is split into two parts. Okay, so the head supplied is given as H static, which is like V1 square minus V2 square by 2, and also head dynamic or pressure head, change in due to pressure. So if H is the total change in the heads, then ultimately this total change can be split into two parts, change in static head and also change in dynamic head, of course. Okay, so therefore this definition is given by R is equal to change in pressure head is how much it is, U1 square, this implies, so this is the basic definition, and R is equal to U2 square minus U1 square minus U2 square by 2G plus VR2 square minus VR1 square by 2G, because this is the change in the dynamic head divided by the change in the total head. Plus U1 square minus U2 square by 2G plus VR2 square minus VR1 square by 2G, because this is the change in total head across a turbo machine and this is the change in dynamic head, of course. Okay, so if you cancel this 2G, because it's a constant, you can cancel it up in all the cases. So it's like this ratios, which is something like R is equal to U1 square minus U2 square plus VR2 square minus VR1 square, this divided with this total H or 2GH is what you can write, where H is the power delivered. Now let's see in case of impulse machines. Okay, so impulse machines में क्या होता है, so let's check it up. We'll classify again. So impulse machines, In case of an impulse machine, you know impulse, what is an impulse? Exerting force for a short time. Okay, so that's called an impulse basically. So in case of impulse machine, जो energy टर्बाइन की एंटेंस पे और टर्बो मशीन की एंटेंस पे अवेलेबल होते हैं वो पूरा काइनेटिक एनर्जी के रूप में होता है. ओके, सो impulse machine is the machine to which the complete energy at the inlet, the complete energy at the inlet is in the form of kinetic energy, is in the form of kinetic energy, is in the form of kinetic energy actually here. Okay, so example, Pelton wheel. So in this case what happens, let's say example, Pelton wheel actually. Okay, so let's see what happens here. Normally when the fluid is entering, यहाँ जो H1 होता है, इस H1 में दो types of energy available होगा, kinetic and also pressure energy. Okay, and as this fluid moves in this turbo machine, some part of kinetic energy gets converted to work, some part of pressure energy gets converted to work, and finally when the fluid is coming out, यहाँ भी fluid के पास kinetic and also pressure energy होता है. Correct? And this H tells you that some part of this is utilized in interaction and some part of this is also utilized in interaction. But मान लो कि एक special case है जहां this pressure energy at the inlet is also same as the pressure energy at the outlet, which means there is no contribution of pressure in interaction with this turbo machine. Yes or no? Correct? ये चीज सबको समझ में आ रही है नहीं? बताओ जल्दी. Are you all clear with this? When this pressure energy at the first section, which is at the inlet, and pressure energy at the outlet both are same, that means the pressure energy of the fluid played no contribution in delivering work to the turbine, or basically do not get any advantage like in case of other turbo machines actually. Okay, so is this clear? Then in such case what happens, the net energy which is available to deliver work is only in the form of kinetic energy. Okay, so in such case the degree of reaction, so if kinetic energy, so when kinetic energy is only participating in energy interaction, when kinetic energy alone is participating in energy interaction, in case of energy interaction, then can you tell me H due to pressure, because you know I have told you H is equal to H static due to change in static head and also due to change in pressure head. Now if pressure energy is not contributing, can someone tell me what happens to this quantity, the change in head due to the pressure? Can someone tell me what happens to this quantity? If pressure energy is not contributing, then whatever the pressure energy is available at the inlet, same is also available at the outlet. Then what is this change in pressure energy? In that case, 0. Correct? So this is 0. Obvious. Correct? So therefore, for impulse machines, this implies degree of reaction R is equal to Hp by total energy, which is H static plus Hp. So in this case, this is 0 and this is 0 and this is non-zero. So ultimately this is 0. Okay, 0 by something is 0. So therefore, this reaction, degree of reaction in case of impulse machines is 0, of course. Okay. In impulse machines is 0. Example like Pelton wheel. In case of Pelton wheel, there is no degree of reaction which takes place. Okay, degree of reaction is basically to the extent to how effective is the pressure energy playing the role in the machine. That's all. Okay, so let's see here again. Then reaction machines. Let's see. Reaction machines, of course. Okay, so reaction machines. So let's look here in the reaction machines. In the reaction machines, the energy available at inlet of the water at inlet of the machine is due to both kinetic and pressure forms. Is due to both kinetic and pressure energy forms. Pressure energy forms actually here. Okay, so they are due to both kinetic and pressure energy forms. Now let's see pressure energy forms. Then ultimately delta this R is equal to H due to pressure by change in head due to static, which is the velocity, and also because this is the total head, so this is static plus the pressure head both. Okay, so change in pressure head by change in static plus pressure head, of course. And in general, depending on the type of machine, we'll see reaction machines like the Francis Arnold Kaplan turbines, all these things. So in that case, so in general, 0 less than R less than 1. Okay, there are exactly 50% reaction machines which we will see, like the Parsons turbine when I'm talking about steam turbines and all. So this R value in reality lies between 0 and 1. So example is something like Francis turbine. That's why Francis turbine has a closed casing. Okay, Pelton wheel bearers doesn't have the casing on the Pelton wheel is just to eliminate the water splashing, because if water is splashed everywhere, then ultimately every surroundings get wet. So just to stop that, it's closed. Okay, but in case of Francis and all, you will see there's a very nice casings which keep the fluid at certain pressure. Okay, so anyway, let's see Francis turbine and Kaplan turbines, all these things. These are reaction machines, of course. Okay, so Kaplan turbines and all. Now lawn sprinkler is also a reaction machine. Lawn sprinkler. Can someone tell me about this degree of reaction of a lawn sprinkler? Any idea? Just if you think for fun. Degree of reaction of a lawn sprinkler, actually. Anyone? Just think. When the fluid is entering this lawn sprinkler, the arm is of uniform cross section. So if the arm is of uniform cross section, then this V1 and V2 are generally same for a lawn sprinkler, if there is no friction and all, of course. So what happens if you have a uniform passage? In that case, this V1 fluid inlet velocity into the sprinkler and fluid exit velocity to the sprinkler both are same, right? Like you have taken the case of a plate. In case of plate, what happens? The entry into the plate control volume and the exit velocity of the fluid chunk is same, correct? Similarly, same thing happens in the lawn sprinkler arms. Whatever the velocity with which it enters, the same velocity with which it generally comes out. Okay, but the rotation is performed because of the change in this pressure head actually. So this change in static head is actually not exactly but almost very small in case of lawn sprinklers. Okay, so degree of reaction of a lawn sprinkler is almost 1. It's 100% reaction. The reason for this is H static. The change in head due to static is very small in this case of a lawn sprinkler actually. Okay, so that's the reason. So these are the reaction machines. Now again, depending upon the direction of the flow, like tangential machines, axial flow machines, okay, radial flow machines, we'll look at all these things as we move forward. But these are the basic definitions which are here. I would like to extend these definitions to some types of efficiencies. So first one, which is a very important for any hydraulic machine, hydraulic efficiency. Hydraulic efficiency, which is also called as eta H, which we will see, or it's sometimes also called as, in case of harness and all, it's also called as wheel efficiency. So let's check it up. Hydraulic efficiency. So what is hydraulic efficiency? So look, if you have a hydraulic machine or turbo machine, generally hydraulic, okay, let's it's a hydraulic machine for the time being. Only the fluid changes. The name hydraulic comes from the fluid is water, that's all. So you have some energy H1, you have some energy H2. So let's say this H is H2 minus or H1 minus H2, for example, for the time being. Then this fluid, when it comes in interaction with this machine, it delivers some energy, of course. Okay. So when this fluid is delivering some energy to this hydraulic machine, the machine's capability in taking energy from the fluid, like this efficiency is defined as head delivered or energy, basically you can write head delivered or energy delivered. It depends because it's a ratio. So head delivered to the rotor by fluid to this to the head available with fluid at rotor inlet. So when this fluid has, let's say for example, some 100 kilojoules of energy with it, okay, in terms of kinetic or pressure, whatever. Now when this fluid is coming in interaction with this turbo machine, what part of energy this rotor can extract from the fluid, that depends upon the machine capability, and this is hydraulic efficiency basically. Okay, so out of total energy available at the rotor inlet, how much energy the fluid solid interaction can transfer to the rotor, this depends upon the capacity of this machine. So this is defined as the hydraulic efficiency, which we'll come across many times. We'll calculate this hydraulic efficiency for Pelton wheel, Francis runners, all these things. Okay, so this definition is a bit important. Then also you have the mechanical efficiency. Normally this is called as the runner power, and normally in case of hydraulic machines, basically if you make certain factors and all multiplications, ROG, all these things, this can be written as runner power. So the power delivered to the rotor or the runner, okay, divided by the power available with the water at the outlet. So it's also called as a runner power by water power in some textbooks like R.K. Bansal and all. If you see, they mention it as runner power by water power. Okay, so mechanical efficiency. First time in my life I'm writing the efficiency spelling wrong. Efficiency. It is denoted with eta m or eta mechanical sometimes. If you want, you can also write this as, some books they write this as runner power, because if you are writing exams like SSC, JEE and all, they follow these local books generally. So water power. So which is nothing but the power available with the water and the power transmitted to the runner. Okay, this same idea. So mechanical efficiency tells something like eta m is, now what happens once you transfer this energy to the rotor, let's say if the fluid and the rotor, the disc are getting in interaction, so the power is transferred to the disc. Now what happens from the disc, the power should get transmitted to the shaft, because in a real power plant what happens, you have a turbine. This fluid will go and interact with this turbine, so that this turbine will rotate. This turbine shaft is coupled to the generator shaft. Okay, so this is the generator. Why you actually want to rotate a turbine? Not for fun, correct? We want to rotate the turbine shaft. We have to rotate the generator shaft. So for this transmission, what happens? This rotor is connected to this shaft by the means of flanges, couplings, and all these things, keys, whatever. So in such case, when power is getting transmitted from fluid to the rotor, there is an efficiency, because the rotor cannot take all the power. At the same time, the rotor, when it's trying to rotate this shaft, because of the fittings, mechanical fittings and all, there is certain losses which occur, okay, because of the pure friction between different rotating elements. So therefore this mechanical efficiency is defined as head delivered, or you can write in terms of power, no issues. Power delivered to the rotor shaft, power delivered to rotor shaft, normally it's called the shaft power sometimes, divided by, we have, so this quantity divided by, we have power delivered to the rotor. Why it's called power delivered to the rotor? Because the rotor can actually give, let's say for example, if 100 kilojoule per energy, 100 kilojoules is the energy available with the fluid, okay, then out of this 100, the rotor got 80, let's say, for example, let's say hydraulic efficiency is some 80%. So 80 kilojoules of energy got transferred to the rotor. Now maximum amount the rotor can give to the shaft is only 80, correct? So that's why this power available with the rotor is same as power delivered to the rotor in the ideal case. Okay, so that's why this definition tells you once the rotor has got 80, now how effectively this 80 kilojoules can be transferred to the shaft. In general, let's say the mechanical efficiency is like 40%, for example. Then out of this 80, only 32 joules can be transferred to the shaft actually. Okay, so this is what it happens. So power delivered to the rotor shaft, it's like a stages. You see, first there is a hydraulic efficiency from inlet to the rotor, then from the rotor to the shaft there is a mechanical efficiency again. Okay, got it. So therefore overall efficiency that you get is overall efficiency. So if you take the total turbo machine as a single unit, then overall efficiency eta overall is equal to, now what is the overall? The initial starting point of this turbo machine is this inlet to this rotor. Okay, so this can be written as power available at rotor inlet and finally what is the last output? This shaft. Okay, so power transmitted to the shaft. After this will get transferred to the generator, of course. Okay, so power transferred to the shaft or power delivered to the shaft. With little manipulation, what can you do? You can write, if you have A by B, for example, you can write this as A by C into C by B, correct? So like that, if I write this expression as power delivered to the shaft by power delivered to the rotor into power delivered to the rotor by power available at rotor inlet. So can I write this overall efficiency as mechanical efficiency multiplied with hydraulic efficiency? Yes or no? Because of this logic. Can I do this? Yeah, because if I split this into two different fractions, then the denominator of the first fraction I am writing this power delivered to the rotor, and also the numerator of the second fraction also I am writing power delivered to the rotor. Then it's like power delivered to the shaft by power delivered to the rotor, which is mechanical efficiency, into power delivered to the rotor by power available at the rotor inlet, which is like the hydraulic efficiency. So this is overall efficiency can be written as product of mechanical with hydraulic efficiencies. Is this clear to all of you? Yes or no? Normally people by heart these definitions, but it's like a staging from stage to stage. What are the efficiencies that gets in the machine? That's all. And many times people feel difficulty in mugging up these things, but don't mug up. It's like first it enters the rotor inlet, then from inlet to the rotor there is certain losses. So inlet to rotor, whatever is the loss that is there, that is calculated in terms of hydraulic efficiency. Then once the rotor got energy, how effectively it is able to give to shaft. That's all. Okay, and sometimes this is called as shaft power by rotor power. All these things are the basic things which we do day in and day out. Okay, is this clear to all of you? If this is clear, we'll go for dimensional analysis, because now we have seen certain basics about the turbo machines, like the concepts of degree of reaction, then impulse reaction machines, velocity triangles. We have seen different definitions like efficiencies and all. So if you want to model the turbine, before we go for Pelton wheel, Kaplan turbine and all, we'll go for some dimensional analysis. Okay, so dimensional analysis for turbo machine in general, if you have any turbo machine. Okay, is this clear to all of you till this point? Please confirm one last time. I'm asking. I'll have some water meanwhile. So everyone, please confirm till this point. Is this clear to all of you? Type कीजिए, it's already 1 hour. Then let's go for modeling. So why do you perform dimensional analysis? Last time कितने बजे तक है? I'm planning to take it like till 12:30 or something, because more than that people generally feel hectic beyond that. Okay, but आज जो concepts है वो इतना tough concepts नहीं है, आसानी concepts ही है. Okay, no more vectors and all. We have already done the vectors and we have got components out of that in tangential direction, so no issue. Okay, vectors में भी मैंने vector calculus, बड़ा calculus नहीं यूज किया ना, थोड़ा सा dot products, cross products, ये चीज यूज किया मैंने. ठीक है, so anyway, let's see dimensional analysis. So when do we go for dimensional analysis? After, I think in basic fluid mechanics, Shivam sir might have covered all the basic dimensional analysis of Alice method, Buckingham's Pythagorean method, then scalings, all these things, dimensionless parameters, Weber number, cavitation, Euler's, all these things he might have done. So I'm just going for the basics. You all know the Buckingham's Pythagorean, right? Okay, Buckingham's Pythagorean is known to you all. Clear? Anyone want a quick revision of Buckingham's Pi theorem? Because I'm going to use that Buckingham's Pi theorem now. If you are comfortable, I'll start straight away with turbo machine. Okay, if you know the techniques. Are you all clear? No repetition, right? No revision, nothing. Can I start turbo machine directly? Yeah. So सीधा मैं turbo machine का apply कर दूँ. Dimensional analysis. You know, kinematic similarity, geometric similarity, then dynamic similarity, ratio of the forces, all these things, correct? So चलिए start करेंगे. So for any turbo machine, the power P interaction depends on certain things. Okay, so let's say fluid is going, all clear? Okay, so we are moving. So power delivered to the hydraulic machine is given by, this power is a function of lot of variables actually. Okay, so normally simply if you see, power is equal to like torque into omega. So ultimately this torque depends upon the force, radial distance, omega, all these things, and this radius is depending on diameter, d by 2, all these things. Okay, but what does this force depends actually? So let's see. Power actually depends upon a lot of parameters like Q. First of all, what is the discharge? Because ultimately if I take a Pelton wheel and if I hit my Pelton wheel with 1 meter with 1 liter per minute, or say let's say 100 liters per minute, there is a difference, correct? Because the power generated by this, let's say for example if you are talking about turbine, in case of turbine what happens, let's say if you have a turbine and if I am hitting the turbine with only 1 kg per second or with 100 kgs per second, then ultimately this heavy discharge can create more impact, correct? So the first thing, it depends upon the Q, discharge. Second, it also depends upon the diameter, correct? क्योंकि जब wheel का diameter बड़ा होता है, so इस component बढ़ेगा, this d by 2 बढ़ेगा and power will be changed. Okay, because if you are impacting on a small machine, torque is very less, but if the same impact if you are doing on a high diameter wheel, then ultimately the impact is more and the power generation increases because this d by 2 increases. Then omega, so it depends upon at what speed this machine is rotating. Okay, ultimately that is needed, at what speed this machine is rotating, that's also very powerful. Then head available, when the fluid is coming, at what head it is coming, means velocity basically. Okay, so if you see at what velocity it is coming, let's say I'm impacting 100 meters per second, I'm impacting 100 meter cube per second, but at only 1 meter per second, a very slow impact. Okay, there is a large fluid but very slowly it's going and impacting, then ultimately power will be low. But let's say if there is a high fluid with high velocity, then power increases. Then it also depends upon the fluid density. Why? Because when fluid is going and hitting, there's a difference. Let's say for example if I take a Pelton wheel, if I hit it with air and if I hit it with water, there is a difference in the impact, right? Because density of the fluid plays a role. And throughout the fluid moving inside the machine, let's say for example you take a for example if you take hydraulic, you take Francis machine. Okay, we'll see the construction, the all the maths involved in that. But normally let's say if there is a blade like this, okay, if fluid is coming in, by the time if fluid is having high viscosity, then the movement of the flow inside this channel becomes difficult. Like for example, I will tell you, you have a runner like this. This is a shaft, something which is located. So this is the rotor and this is the shaft, a rotor shaft. Okay, and you have the vanes, let's say vanes like this. Okay, so that this is rotating, this is rotating. So when this is rotating, ultimately मान लो कि जो fluid अंदर जाए, वो high viscosity का fluid है. So when fluid's viscosity is high, the passes in this will definitely depend, and the loss due to the loss in the energy in this path will also decide the velocity at the exit. So velocity triangles will change. Okay, so the power calculations will change. So it also depends upon mu, of course. And right now I'm not discussing much, but there is also one parameter. If you are dealing with compressible flow machines like compressors or steam or gas turbines, in such cases it also depends upon E. What is E? Bulk modulus. Okay, when you have the compressibility effects, E is the bulk modulus actually. Okay, so E is the bulk modulus. And of course, there are other terms as well, but these are the main things which we are restricting as of now. Now, dimensional analysis is one very powerful tool to reduce the number of parameters. Okay, so here total you have how many? So there is a function. So if you want, you can write it as function of power, discharge, diameter of the jet, speed of the water, head, rho, mu, E is equal to 0. This is a function. Now, how many variables are there in this? 1, 2, 3, 4, 5, 6, 7, 8 variables are there, correct? So, total number of variables involved. Variables involved is equal to 8, of course. Okay. So, ठीक है, हमारे पास 8 variables हैं. Now let's see in this 8 variables how many dimensions, fundamental dimensions are involved, correct? वो check करना पड़ेगा definitely. So let us write the dimensions of each quantity. So power. So power का dimensions क्या होगा? So power can be written as force into velocity. So what are the dimensions of force? Mass into acceleration, meters per second square into velocity, L t power minus 1. So m L square t power minus 3. This is going to be the dimension for force, correct? So normally if you take power can be written as force into velocity, and force can be written as mass into acceleration, meters per second square, into velocity, meters per second. So m L into L square t power minus 3. So this is m L square t to the power minus 3 is the dimension of this. Okay, then fine. So next, what about discharge Q? So Q is meter cube per second. So L cube t power minus 1. L cube t power minus 1. Okay, then diameter. So D, इसका क्या होगा? Meter. L, N, rotation. So rotations per second, number of rotations per second. Number of rotations is not having any unit, you will just count. So time inverse per second. Okay, rotations RPM, rotations per second, rotations per minute. So number of rotations is just a number, you don't have any units, you will just count. Per minute or per second will give this t power minus 1. Okay, then coming to GH. So what are the dimensions of GH? So G is acceleration into gravity, meters per second square, into 1 more meter. So meter square per second square. So L square t power minus 2. Then dimensions of density, kg per meter cube. Dimensions of viscosity, kg per meter second in MKS, kg per meter second. Okay, then bulk modulus. So what are the units of bulk modulus? Any idea? Bulk modulus, same as Young's modulus, all these things, correct? It's just a modulus value. So pascals. Okay, so the units of this is pascals, Newton per meter square. So which gives you m L power minus 1 t power minus 2. Is this clear to all of you, these dimensions, which you might have seen, except maybe the Young's modulus is for the first time you're seeing, but rest of all everyday known stuff. Okay, now there are 8 variables in this function, but the number of fundamental dimensions involved when you put these 8 variables together is only 3 dimensions. In this complete dimensions, apart from mass, length and time, can you see any other dimension which is involved? You have total 8 variables and involving 3 fundamental dimensions. So number of pi terms, if you use Buckingham pi theorem, okay, so therefore total number of variables is equal to 8. Number of fundamental dimensions involved, number of fundamental dimensions involved is equal to 3. Okay, because only mass, length, time are involved, nothing beyond that. So if total number of variables is 8 and these 8 variables are involving only 3 fundamental dimensions, when you put all these things together, apart from mass, length, time, you cannot see any other thing. So therefore number of pi terms, how many do you have? Number of pi terms is going to be how many? Any idea? कितना pi terms आएगा? Total 8 variables है और वो 8 variables 3 fundamental dimensions involved कर रहे. So total number of dimensionless terms or the pi terms basically is how many? 5, correct? 8 minus 3. Right? So total we have 5 dimensionless terms. Now to do this dimensional analysis, we have to choose the repeating variables. Of course, I'm using the Buckingham pi theorem, so we need the concept of repeating variables. So we have to fix this repeating variables. repeating variables. So how many repeating variables we have to choose? These many, correct? Number of fundamental dimensions involved in the problem should be same as the number of repeating variables. So how to pick the repeating variables? This is the first question. So any idea? So you know the rules for picking the repeating variables. So out of these repeating variables, what you pick? One variable should definitely deal with the geometry of the problem. Like let's say if there is a flow in a pipe, okay, then diameter, because diameter decides the flow. If your flow is in a square cavity, then ultimately one of the dimensions for scaling, okay. So one repeating variable should definitely involve the geometry of the flow, okay. So here, out of these parameters, the parameter which deals with the geometry of the flow is d, diameter. So I am picking d with this. This d is actually dealing with the geometry of the flow or geometry of the problem, diameter of the disc or runner, whatever, okay. So geometry of the problem. Next, one variable should definitely deal with the kinematic conditions of the problem, because when geometry, flow, fluid, yeah, of course, okay. So one parameter should deal with the kinematic conditions of the problem. So out of these kinematic conditions, the easiest kinematic condition is the speed. Why I am taking the easiest? Because these variables keep repeating in all the dimensionless terms, okay, in all the analysis. So if you take a variable with higher dimension, so उस higher dimension को higher pi term पे calculate करना पड़ेगा. So थोड़ा सा calculation lengthy होता है. So इसलिए we are trying to make out the terms with less number of dimensions, but also satisfying the kinematic condition. So this is n, kinematic conditions. So this is for the kinematic condition of problem. It involves with the kinematic condition of the problem, and also all these are input variables, okay, we can change them. Then last is property of the fluid, okay. So property of the fluid, we have multiple things: density, dynamic viscosity, bulk modulus. You can take anything, but out of these three things, this has the simplest dimension, so I am taking rho, that's it, okay. So rho, this talks about the property of the fluid. So when you are making the choice of repeating variables, definitely एक variable geometry of the problem को define करना पड़ेगा, दूसरा kinematic conditions को define करना पड़ेगा, और तीसरा fluid properties को define करना पड़ेगा, ठीक है. So this D, N and O, and after making this selection of repeating variables, it's not like, since these three variables are satisfying this geometry, kinematic condition and property of the fluid, you can always take one important check you should do is, if you look at the dimensions of these three, so diameter, length n, T inverse and rho, kg per meter cube. So this is what you have. These are the dimensions. When you put these dimensions together, the dimensions here should involve all the dimensions involved in the problem, okay. So मान लो कि मैंने repeating variable select किया था, लेकिन मान लो कि उसमें time नहीं है, okay. If you mix these three, there is no time, then you cannot make that choice, okay. That choice is not valid. If you make dimensional analysis with that choice, you will get wrong dimensionless numbers, okay. So after making this choice, you should check for the completeness of the dimensions actually, okay. When you put these three things together, this dimension variables should involve all the dimensions involved in the problem, and here you have M, you have L, you have T, that's it, okay. So all these are variable, all these are valid, so you can make this choice actually. Clear? There is a, it's not like you pick, I like density, I like diameter, I like n, so I pick them. There is certain logic behind building up this repeating variables actually, which is very important, okay. Now let's see if these are the repeating variables. So let's start our dimensional analysis now quickly. So pi terms, okay. So let's see the first pi term. If you calculate, pi 1 is equal to, let's say, d power a, n power b, rho power c. So what are the variables? So first variable, power, let us take power p, okay. This is the first dimensionless term. So this implies pi is a dimensionless term, so you have m power 0, l power 0, t power 0 is equal to diameter l power a, speed t power minus 1 power b, kg per meter cube. So kg per meter cube is how much? M l power minus 3 power c into, what is the dimensions of power we have seen? M l square t power minus 3, m l square t power minus 3. So if both sides has to be same dimensions, ultimately we get power of m. M has only power 1. This is power 1 of course, because this is of power 1 clearly. So this is m and this is c. So m has, and there is no m in these two. So m has total power of 1 plus c. So 1 plus c is equal to 0. Then coming to L, 2 minus 3c plus a is 0. Coming to T, minus 3 minus b is equal to 0 of course. Okay. So we have the equations with the unknowns. You can calculate c equal to minus 1. If you put c equal to minus 1 here, a equal to minus 5, then b equal to minus 3. That's it. Okay. So this implies the first pi term is going to be d power a ka value minus 5, n power b, so b ki value minus 3, rho power c into p. So this implies the first pi term is going to be p by rho n cube d power 5 actually here. Okay. So that's the first dimensionless term that you got, p by rho n cube d power 5. So let's calculate the second, because you have total 5 pi terms. Let's calculate all the 5. So pi 2. So let us calculate. So pi 2 is equal to again d power a, n power b, rho power c. So what is the next variable we can take? So q is also not covered, so q we can take. So q, this is what you have. Okay. I'm just doing dimensional analysis. You guys know this very much. A bit of fun stuff to do. So let's do this dimensional analysis. So m power 0, l power 0, t power 0 is equal to l power a, t power minus 1 power b, rho kg per meter cube power c into discharge meter cube per second, meter cube per second. Okay. So this is meter cube per second, L cube t to the power minus 1. Now if you compare both sides, c is 0 ultimately, correct? Because mass is only in this term, there is no other term, 0. Length a minus 3c plus 3 is equal to 0. So c is 0. So a is minus 3. Then time. So what is the time actually? Minus b minus 1 is equal to 0. So b equal to minus 1. So b equal to minus 1. So what does the term imply now? Therefore pi 2 is equal to d power a, n power b, rho power c, c is 0 times q. So q is, rho power 0 is 1. So the pi 2 second dimensionless term is going to be q by n d cube is what you have. Okay. So q by n d cube is what you have here. So q by n d cube is the second dimensionless term. Okay. Is this clear to all of you? Are you all understanding? This is a simple, since you are confident about the Buckingham pi theorem, I am just applying the things. Okay. We have total 8 variables, we have total 5 dimensionless terms, 2 we have calculated, remaining 3 भी हम calculate करेंगे. ठीक है? Yes or no? Is this clear to all of you? Please type it in the chat box. Till this point, is this clear? If this is clear, we'll do quick analysis of other 3 dimensionless terms. Okay. Now let's see pi 3 term. Pi 3 is equal to d power a, n power b, rho power c. What's the next term? Let's check it. So d is completed. Already we have taken the repeating variables. N is also finished. We have taken gh. So let's take gh to be the 4th term. Gh. Okay. So let's do the dimensional analysis again. So m power 0, l power 0, t power 0, l power a, t power minus 1, kg per meter cube. So kg per meter cube into dimensions of gh is g is l t power minus 2 and this, so l square t power minus 2. That's what, correct? So meters per second square into meter, so meter square per second square. So let's compare the things. So if you compare, mass is only in this, so c is 0 again. Then time or L, a minus 3c plus 2 is equal to 0. So c is 0, so a is minus 2. And time minus b minus 2 is equal to 0. So b is minus 2. That's it. Okay. So this is what you have. So therefore the pi 3 term is equal to, let's go directly, d power a. So a is minus 2. So there is a d square in the denominator. N power b, b is also minus 2. D square, n square. C is 0, so there is nothing, gh. So gh by n square d square. So this is the 3rd pi term actually. So pi 3 is gh by d square n square. So let's go for the 4th pi term. Let's calculate quickly. So what is the fourth pi term? Pi 4 is equal to d power a n power b rho power c into density is already taken, so dynamic viscosity mu. So this implies m power 0, l power 0, t power 0 is equal to l power a t power minus 1 kg per meter cube into kg per meter second. Okay, this is the dimensions. So if you simplify this, this implies let's check, mass is in both these terms, so c is minus 1, okay, because 1 plus c is equal to 0. Then L is how much? A minus 3c minus 1 is equal to 0. So if c equal to minus 1, if c is equal to minus 1, 3 minus 1, 2, so a equal to minus 2 taken. So what is the value of b then in that case? Minus 1, no, minus b minus 1 is equal to 0, so b is minus 1. Okay, so b is minus 1, correct? So if you minus 1 plus 1, yeah, 2. So what is the pi 4 term? Therefore pi 4 is equal to, let's see, mu by then d power a, so a is minus 2, so there is d square, n power b, so b is minus 1, so there is n, and we have c power minus 1, so this is rho. So pi 4 is mu by rho n d square actually here. Okay, so this is the fourth pi term. Let us go for the last pi term calculation, which is pi 5. Pi 5 term. Why I am doing all this, you will come to know very soon. Okay, we have some important parameters which we will bring out. So pi 5 is equal to d power a n power b rho power c. What is the last variable that we have? Bulk modulus, no? So e, yeah, bulk modulus is what we have. So if you look at the dimensions, m power 0, l power 0, t power 0 is equal to l power a t power minus 1 power b kg per meter cube power c into, what about e? E has the dimensions, e is the bulk modulus, it has the dimensions m l power minus 1 t power minus 2. Okay, so m l power minus 1 t power minus 2. So if you simplify this, 1 plus c is 0, so c is minus 1, then a minus 3c minus 1 is also 0. So when c equal to minus 1, a equal to minus 2, correct? So equal to minus 1, so 3 minus 1 is 2, so a plus 2 is 0, so a equal to minus 2. Then what about b? T minus b minus 2, so b is minus 2, that's it. Okay, so if you simplify this, therefore the pi 5 term is going to be e divided by d power a, so d square, n power b, which is n square, and rho power minus 1, so this is rho, that's it. So we have these 5 dimensionless terms for any turbo machine in general. So for any turbo machine, these are the 5 terms actually here. Okay, so e by rho n square d square, so these are the 5 terms. A simple Buckingham pi theorem analysis, we got pi 1, pi 2, pi 3, pi 4 and pi 5. So therefore this function, which is implicit like this, therefore for f of p q n d gh rho mu e, these are the parameters, correct, is equal to 0. This implies, with dimensional analysis with reduction of variables, some function of the terms pi 1, what is pi 1? P by rho n cube d power 5, correct, q by n d cube. Then third term, what is the third pi term? Gh by n square d square. Then fourth is something like mu by rho n d square. And what is the fifth? E by rho n square d square is equal to 0. So we have reduced this to 5 dimensionless terms actually, which is 5 pi terms actually. Now one important thing is, like we have done almost in 5 minutes. 10:28 is what when I have started doing the dimensional analysis. Then we have done almost like 1 minute for each term. Okay, so let's see, in this case, can someone figure out what is this number? Something known to you, mu by rho n square rho n d square, that number is something known to you. Can someone understand something? What is that number? No, yes, you all know this. It is some number. Reynolds, yeah, correct. Reynolds number. Reynold. Okay. Reynolds. Reynolds. ओके Reynold रेनॉल्ड्स नंबर. टर्मिनोलॉजी बहुत इंपॉर्टेंट है, ठीक है. फ्लूइड मैकेनिक्स में सबको पता है कि रेनॉल्ड्स नंबर बहुत आसान का बहुत फेमिलियर नंबर है. सो अगर मान लो कि इसका नाम भी लिखना नहीं आता तो इंटरव्यूज में थोड़ा दिक्कत आएगा. दे विल प्ले विथ यू. ओके. I don't want to hurt anyone, but generally please start learning things, okay? Otherwise it's because सबको पता है कि ये नॉल नंबर होगा, वो VD by mu, ये सब हमको पता है, लेकिन प्रॉपरली प्रेजेंटेशन करना भी बहुत इंपॉर्टेंट होता है, ठीक है. चलिए, क्योंकि इन द नेक्स्ट 1 year यू ऑल आर गोइंग टू अपीयर फॉर PSU इंटरव्यूज एंड ऑल दिस थिंग्स. चलो, दिस इज रेनॉल्ड्स नंबर, क्योंकि म्यू बाई रो VD, बट V कैन बी रिटन एज ND of course, okay? So this V and ND has the same dimensions, of course, meters per second and meters per second actually. Clear? So that's what. So this is a Reynolds number actually, or 1 by Reynolds. Does someone know what is this number? किसको पता है वो नंबर क्या है? ये कौन सा नंबर है? E by O and square D square. ऑयलर? नहीं 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 नहीं, ऑयलर नंबर नहीं है. If you take a square root of this actually, because if a number is dimensionless, square root of that number, square of cube of fourth, for whatever you take, it's a dimensionless, correct? मान लो कि A is dimensionless, then A square is also dimensionless, square root of A is also dimensionless. This is, if you take square root of this, because you know if A is dimensionless, 1 by A is also dimensionless, so this is actually Mach number, velocity by acoustic velocity. Have you all studied acoustic velocity is equal to square root of E by O in basics of compressible fluid? I think Sam might have taught you. A is equal to square root of isentropic bulk modulus by density of the fluid, or in thermodynamics at least. Many people, I generally teach it in thermodynamics. So because to do this thing we need certain, and normally for ideal gas this is equal to square root of gamma RT. This is only for ideal gas, but this is for any substance in general. मान लो कि स्टील है आपके पास, ओके? अगर स्टील में एक टैपिंग किया तो वेलोसिटी ऑफ प्रोपगेशन ऑफ साउंड, Mach number, yeah, okay? You know this, like normally in general this is something like isentropic pressure constant, so which gives you isentropic by density of the flow actually. That's what they give you, okay? This derivation is a bit nice thing to know, okay? Because velocity of propagation of sound in any, or velocity of propagation of disturbance in any medium is given by this value, okay? For ideal gas this value becomes gamma RT. You all might have seen A equal to root gamma RT, no? This you might have known, but this is only for ideal gas, and there are questions in gate mechanical also based on this, okay? So this is for ideal gas, and this is for any substance in steel, rubber, liquids, anything. You have this, okay? Normally I'll just show you a glimpse maybe if you are interested. I taught thermodynamics recently to, I think 2 months back I taught to some English batch students. Entropy, exergy, relations, yeah, thermodynamic relations. Joule-Thomson coefficient, all the graphs and all. So this is basically the change in enthalpy calculation for any substance. You know why enthalpy of ideal gas depends only on temperature, all these things. This is Mayer's equation, you know, this is the Mayer's equation basically, TV beta square by KT. This is the Mayer's equation, and this is for any substance at any state, and for ideal gas this becomes characteristic gas constant. That's it, okay? So this is for any substance, and this is how we have seen a bit of simple Simple ideology. If you follow, there is nothing complicated in this, and that's what I have shown. So for ideal gas, this TV beta square by kT term finally comes up as R. Okay, this TV beta square by kT for ideal gas will come up as characteristic gas constant. So that's the ideal gas equation. I didn't teach or what? Generally I teach. So let's see some other. Here it is. So you can check. So basically acoustic velocity. Okay, acoustic velocity, disturbance. So if in a medium, if you create a small disturbance, then what happens? This wave, if there is a piston, if you give a small push, then this wave gets developed and this wave moves in this medium at acoustic velocity A. So by doing simple mass conservations, okay, then energy conservation, you know, steady flow energy equation basically. So if you apply, then here you can see within a simple 1-2 steps we achieve this point. Okay, so root of dP by dO ES, and from definition of bulk modulus, you know, we can write this as A is equal to root of ES by O, because you know this is the definition for bulk compressibility and bulk modulus. So we can write this. So this is what we have. Now for ideal gas, what happens? We have taken the assumption of ideal gas. For ideal gas, you can see this is root gamma P by O. They have done some analysis, and no, here I have done the analysis. Okay, so for ideal gas, P O power minus gamma equal to constant. So you will eventually show that this is equal to root gamma RT. Okay. So anyway, this is the basic thing, but Mach number is something like velocity, actual velocity of the flow by velocity of the disturbance in the flow at that point. Means let's say some fluid is flowing, that's the some liquid is flowing. Okay, that is the actual velocity of the liquid. Now in this liquid, at that condition, if you create a small disturbance, at what speed the disturbance travels inside the medium, that is the acoustic velocity. Ratio of these two is Mach. Okay, so anyway, let's see. Okay, let's leave it like this. So this is like basically Mach number, and these are the dimensionless numbers. Now in case of hydraulic machines like Pelton wheel, Francis harness, Kaplan turbines and all, we don't take the effect of compressibility generally. Okay, and also for the simplicity in the gate and ESC level, what they do, they don't also consider the viscous effects in general. Okay, so therefore for hydraulic machines, E by rho n square d square is neglected because the fluid is water, and also the Reynolds number mu by rho n d square is less significant slightly. But of course, mathematically, if they want to give, they can give. Okay, I think in XC 1 year in 2023 or somewhere they have given with the consideration of Reynolds number also, because mathematically it's a dimensionless number which exists. Okay, so there is one question which was asked on the modeling of the turbine based on the Reynolds number in that year in 2023 XC. Okay, so these two terms are generally a very small terms which can be neglected. Okay, so in general, if you see, in general, the function of P by rho n cube d power 5, okay, then Q by n d cube and GH by rho n rho is not there, n square d square is equal to 0. This is the function. So this is like pi 1, pi 2, pi 3, you know. Excuse me, sorry. So you have things like pi 1, pi 2 and pi 3. Okay, now try to tell something here. I am considering something. Look what happens. Consider pi 1 power 1 by 2 by pi 3 power, if I want to eliminate the diameter, this is like 5, so this is like 2, so 5 by 4 is what it comes. Okay, so yeah, this is 5 by 4. So let's say I'm considering these terms. So what does this combination give you? Let us check for some time. So pi 1 whole power 1 by 2 by pi 3 whole power 5 by 4. If you do this calculation, let's see. Pi 1 is like P power 1 by 2 by rho power 1 by 2, n power 3 by 2, d power 5 by 4. Sorry, 5 by 2. Okay, this is what we have. Divided by pi 3 power 5 by 4. So if I want to model this, g power 5 by 4, h power 5 by 4 by n power 5 by 4 into d power, sorry, n power 5 by 2 actually, into d power 5 by 2 actually, correct? This is what you get. Yes or no? Is this clear to all of you till this point? Please type it in the chat box. Pi 1 whole power 1 by 2 by pi 3 whole power 5 by 4 actually. Okay, so please type it in the chat box. Is this clear to all? P power 1 by 2 by O power 1 by 2 n power 3 by 2 d power 5 by 2 by g power 5 by 4. Is this clear? Just I am taking this ratio. This is pi 1, this is pi 3, so pi 1 power 1 by 2 by pi 3 power 5 by 4. Okay, yes or no? Please type it in the chat box. Yeah, now if you simplify this, let's see what it comes. D power 5 by 2 and d power 5 by 2 cancels. Okay, the main intention 5 by 2 or 5 by 4. There are squares now. So n square whole power 5 by 4 gives you 5 by 2. Okay, that's why when you do 5 by 4 here, these two terms will get 5 by 2s because of this. Okay, n square whole power 5 by 4 is 2, 4 gets cancelled twice, and you have n power 5 by 2 of course. Okay, that's what. Fine. Okay, as fuck. Okay, now let's see, if you have these things, then diameters gets cancelled. Now once diameters gets cancelled, also you can observe one more thing. This n power 3 by 2 will cancel this n exactly, correct? Because n power 3 by 2 by n power 5 by 2, so ultimately you have n of course. So if you write this, we have, you know, a by b by c by d. I can write as a by b into d by c. So p power 1 by 2 by rho power 1 by 2 into this term which is in the denominator, I can write it as n upon g power 5 by 4 into h power 5 by 4 of course here. So if you observe this, this is something like n root p by root rho into h g power 5 by 4 into h power 5 by 4 actually here. Okay, so this tells you something about some quantity. It's a dimensionless quantity of course. N root p by root rho into g power 5 by 4 into h power 5 by 4 actually here. So it tells you about something. It is a dimensionless quantity. Ultimately you have done dimensional analysis. If you have a turbine which has some power requirement, let's say for example you are putting a power plant, then you know you decide that okay, my turbine has to provide this much power, you know this, and you have also decided the diameter. Now to test that in lab, ultimately you have to bring down the scale, because in lab you cannot build a very big turbine. Okay, so you can build a small model, but depending on the head available, and if you want to develop the power, if you want to calculate the power generated by the model, you have to make some dimensionless number equal. The issue with this is it has diameter and n, but it don't have head, because the turbine power generated depends on the head actually. Okay, so we are connecting this term with this. Okay, for turbines. Okay, so consider for turbines I am doing this. Okay, any turbine in general, hydraulic, gas, anything. So in case of turbines, hydraulic and turbines, in case of any hydraulic turbine, main idea is to calculate what is the power developed by the turbine and also what is the head available with the turbine. Okay, but there is no dimensionless number which is connecting these two. So what I am doing, I am trying to find a dimensionless number, a new dimensionless number using these two, such that, because if this is dimensionless, power 1 by 2 is also dimensionless. If pi 3 is dimensionless, power 5 by 4 is also dimensionless. You take a ratio, multiply, add, whatever, the outcome is still dimensionless. Okay, I am trying to design a dimensionless number such that which connects my power and also head, but it is independent of the diameter. So I can design my model at any scale, doesn't matter. Okay, did you understand why I have taken this? I have taken this constants 1 by 2 and 5 by 4 exactly such that this diameters gets eliminated. That's it. Okay, so diameters get eliminated, and also this power on the n becomes exactly 1. So it tells you of a particular dimensionless number where the scaling, where there is a scaling of power and head simultaneously, irrespective of the size of the diameter. Okay, so you can conduct experiment on this much diameter wheel or this much diameter wheel or a very big diameter wheel also, doesn't matter, as long as this dimensionless number is made equal between the model and the prototype, results match. Okay, so this is actually called, it is actually speed, and this is normally called specific speed, or I think many of you are familiar with ns. So nst, or let's call this to be KST first of all, KST. So this is basically it's a dimensionless number, dimensionless specific speed. dimensionless specific speed. Now, if you observe something, in a hydraulic machine, generally we use water, so this quantity is fixed. In a given place where you are doing testing and all, normally on earth anyway, on an average, this G is also constant, okay, G power 5 by 4. So this is something like constant. This part which is here is constant almost. So some K, which is constant in model, prototype, everything, okay. Let's assume if you are doing the, normally if you want to test a hydraulic turbine and water is the cheaply available fluid as of today. So if you are doing testing in the lab with water, so in the prototype and in the model, you are doing same testing with same fluid. G is same in both the cases. So anyhow, by default, whether you put it or not, this quantity is going to be same in both the cases, model and prototype cases. Therefore, we define something called NST, which is equal to N root P by H power 5 by 4. So this is called as dimensional specific speed. And how this is obtained? By taking out this constant, which is constant in model and prototype. So this is dimensional specific speed. And if you want to model a turbine, we'll make sure this term is equal between the model and the prototype. And we'll make sure, normally the class of turbines depends on this NST values actually. Okay, so this NST plays a very important role in deciding the power of in deciding the type of the machine which you want to impart, depending on the experiments, lot of literature that we have as of today. So this NST plays a very crucial role in deciding the nature of the turbine that you're going to put actually in the install in a place actually here. Okay, so that's how this N root P by 5. It's not like since I love pi by 4, I love 1 by 2, I'm doing this constants. So this is what you have actually. Clear to all of you? Now did you understand why I have done dimensional analysis to figure out things? Okay, so this is the speed at which the machine should run to generate 1 unit power under 1 unit head, because if you want to take NST equal to N, you should make this P and 1, H as 1. So that tells you that NST specific speed is specific speed of the turbine. Specific speed of the turbine is the speed at which the machine or the turbine runs, speed at which the turbine runs to produce 1 unit power under 1 unit head. Under 1 unit head actually, like this. Okay, so KST and NST again. This KST is dimensionless. Okay, क्यों? Because ये दोनों dimensionless है, so इसकी वजह से ये भी dimensionless होगा. लेकिन इस dimensionless number में density of the fluid, if you do testing with water and G is constant everywhere, so these things can change. N, P, H can change, but these two things generally do not change. Okay, they are fixed. So इस constant को हम हटाते हैं यहाँ से. So we get this N root P by H power 5 by 4. Okay, so this has some dimensions obviously, because we are disturbing the dimensionless term by deleting some terms. So this has got dimensions obviously. So this is normally called as the specific speed in dimensional form. Okay, how many have seen this for the first time from dimensional analysis, and basically what's happening you might have understood now? Have you seen this before anytime? Okay, some of you might be seeing it for the first time, no? Definitely. So obviously if this is like, just a second. First time you are seeing. In my class it happens many times, you'll see for the first time the understanding, because I'm telling this after getting the feedback after teaching fluid mechanics. Almost like I have taught fluid mechanics like almost some more than 25 times, to be frank. Okay, so because for the past 7 years on an average, even if I'm teaching 3-4 batches, yeah, of course easily I'll teach. So it's like almost some 20, easily 25 batches I think I've taken. Okay, and this is like an advanced part of that. Slightly, it's not advanced. Advanced is something which is complicated. It's just like an extension. Okay, extension is the same difficulty but going 2-3 steps forward. That's it. Okay. Thermodynamics, so I have taught around some 20 plus batches till now. Okay, heat transfer I did not teach after coming to BW, but before that I have taught some 7-8 batches around. Okay, these things happen. ATD is again many times I have taught, and in English batches applied thermodynamics is going to start from Tuesday, I think. Yeah, from Tuesday. 27 is Tuesday, no? Yeah, so from Tuesday I'm starting applied thermodynamics there. Okay, to be frank, from turbo machines there is no question in GATE exam for past 3 years. 2022 no question has come up in turbo machines. 2023 no question has come. 2024 also no question has come. Okay, so the probability of having question this time is high actually, since it's not there in the last 3 times. Okay. Okay, so this is dimensional. It has dimensions obviously, because you are disturbing the non-dimensional term by deleting some terms and all. So obviously the dimensions get disturbed, and there is dimension for this. Okay, and normally if you see, okay, I'll give you at the last maybe, but the details after teaching the turbines, because right now we don't know what is Francis, what is Pelton wheel and all. So similarly you can understand one more thing. For pumps, what happened? Look, for pumps or compressors, these things, for pumps or compressors generally, whenever you calculate this thing, okay, so in case of turbines, the amount of power generated is the main point of interest. Okay, but in case of pumps, what is the high pressure discharge? Means how much amount of discharge is given by the pump. That's the main crucial crux, and to what head it is getting delivered. Okay, these are the 2 things. So again, if you make an attempt to delete the diameter, it is like d cube and it is like d square. So consider pi 2 and pi 3. Let us decide the powers. Okay, so power 1 by 2 to delete this diameter, and then if you do power 1 by 2, you have diameter power 3 by 2. So diameter power 3 by 2. So to eliminate this d power 3 by 2, so you have d power 3 by 2, then you have d square whole power x if you want. Then you have, if you want to delete this diameter, 3 by 2 should be equal to 2x, then x should be equal to 3 by 4. Okay, so this is 3 by 4. Okay, so it should be 3 by 4. So then diameters gets eliminated obviously. So let's see pi 2. So what is pi 2? Of course, pi 2 is this q by nd cube, because discharge is the main point of interest, and to what height it is getting delivered. That's also some nice thing to look at. So if you simplify this, we have root q by okay, first let's write it in terms of powers. Q power 1 by 2 by n power 1 by 2 d power 3 by 2 upon g power 3 by 4 h power 3 by 4 by n square power 3 by 4, so which is like n power 3 by 2 and d power 3 by 2. Yeah, of course. So if you again eliminate the diameters, because you want something in irrespective of the size, because you have different space limitations at different locations, so you don't want a dimensionless number which involves diameter. So if you delete this, then this gives you n again. So this is something like root q by g power 3 by 4 h power 3 by 4 into this n will go to the top. That's it. Okay, yeah, that's all. So it's like n root q by g power 3 by 4 into h power 3 by 4. That's what you have. Okay, so this is again dimensionless number in terms of for pumps. Okay, so therefore KSP, this is called KSP, which is something like dimensionless specific speed. It has dimensions, but again in case of pumps, wherever you design the development model and do testing, this fellow is constant. Okay, so it is acceleration due to gravity, it's constant everywhere, no issues. Okay, so therefore we define something called NSP, which is n root q by h power, how much it is, 3 by 4. Yeah, This is 3 by 4. So n root q by h power 3 by 4. So this is basically the dimensional specific speed. And again, when you are talking about the selection of pumps and turbines, all these things, so dimensional specific speed. So when you are doing analysis based on picking up a pump, picking up a turbine, this we have charts based on the KSTs, or sorry, NSTs and NSPs. So it's like the net specific speed. Yeah, basically it is like it's called the specific speed. It's net. Okay, we'll see what is net and in detail, net, positive, suction head, all these things in maybe in the next week's class. But right now this is what you can keep it. Okay, so if you want to design a pump, this term is actually very helpful. Okay, so these are the things which I thought of doing in the dimensional analysis, which makes you understand the thing. Okay, like cube and a cube, whenever you have they give you head, all these calculations, it would be helpful. So let's see, let's solve one question maybe based on our understanding till now, then we'll start Pelton wheel. So solve this question. A turbine operating under a head of 32 meters develops 9000 kilowatt at a speed of 100 rpm. If the head on the turbine is reduced to 16 meters, okay, this will solve maybe after teaching something called unit speeds and unit quantities. Okay, so solve this question. The ratio of forces exerted by water jet when it is made to strike a stationary flat plate held normal to it, flat plate moving in the direction of the jet, equal to 1/3 the velocity of the jet. Come on, solve this question. MCQ, so single choice. Say I'm giving you 2.5 minutes. Start. Solve this question. It's a very easy question. Just impact of jets. Again, some homework question. So please solve, because it's been like 2 hours. So if I keep teaching the story, then you will get bored. So solve this. What is the significance of that speed term? See, that term denotes the power and head combination, which should be made equal between the model and the prototype actually. Okay, so if you are picking a turbine for modeling, we make sure this NST term, what is coming, that should be made equal between the model and prototype. Like for example, you decide to operate your turbine at a head of 500 meters, okay, and in lab you are testing. Then for the complete power requirement, you will check at what speed you should run the machine so that the scaling matches. Okay, so which when we go into some in-depth of pumps and all, or basically turbines and all, we can observe. But in general, that NST term should be made equal between the model and the prototype actually. Okay, so because that connects the power and head scaling accordingly. Fine. So let's solve this question. The ratio of forces exerted by water jet when it's made to strike a flat plate. So let's say if there is a flat plate like this, which is fixed. So F is equal to OA V square, V jet square. Okay, and this is in stationary. When the jet is, when it's moving, if this plate is moving with velocity u, and if the jet is following with Vj, Oj, Vj minus u square, correct? This is what you have. Then they are asking you the ratio. And u is given as 1/3 the velocity of the jet. This becomes Vj square by Vj minus 1/3 of Vj, it's like 2/3 Vj square, so which is 9/4. That's it. Okay. Simple question based on the jets. Good, 60% of you have answered correctly. Nice. Pankaj knows it in 3 seconds. Good. Somehow. Okay, fine. So this is 9/4. You forgot the square. Okay. People who are 3/2. So let's see. Let us go for a discussion on Pelton wheel. Okay. And I'd like to add one statement here before I go to the Pelton wheel. NST plays a crucial role in deciding the type of machine to be used. Normally we'll also see that the ranges are there for the value of NST to be chosen. Like if the value of NST is something, then we'll choose a class of machine from the available machines. Normally in market, if you want to go, they'll have this NST based charts. Okay, so they'll ask you what is the specific speed. Normally they'll ask you the power requirement, all these things. Then they'll ask you what is the specific speed also. Okay, so once you normally if you open any pump, I'll maybe show you one if I can show you. Pump, specification plate. If you check, so pump data plate, if you check, so like for example you open any one, okay, this one, so it's of a centrifugal pump. Okay, so if you check this, normally the phase and voltage is there, obviously a bit of electrical thing. So the pump power, then size and speed at which it operates. So basically this speed, discharge, all these things, they get correlated. Okay, and this is of course once the pump is done, but initially to select, if you have the charts, then pump charts, turbine charts, we have pump chart. Okay, so pump charts, if you see, they'll give this NST on one scale and they'll ask you for the other maybe, but okay, in next class I'll try to put it in the PPT in detail. So normally we work for selection of pumps many times, so then we use all these things. Okay, so let's apply now these things. So this is the total fundamentals about the turbo machines. Either you use a pump or compressor or turbine, anything. So now that the main core part is done. Okay, now we'll apply this simply to each of these devices, like Pelton wheel, then Francis Arnold, Kaplan wheels, all these things. Okay, so let's see Pelton wheel. So what we have for a Pelton wheel, let's check. Pelton wheel is first of all an impulse machine. Like as I told you, it's a tangential flow impulse machine. Impulse machine. It is generally kept open to atmosphere. There's a small glass casing or plastic casing in many times. The main job of the casing is just to stop the spilling of water, because what happens if a wheel is rotating and if you impact a water jet on it, then what happens after the impact, the water splashes all over. Okay, so to stop the water splashing all the places, they put a little bit of casing, but that casing is not to control any pressure or something. Okay, so let's see how do we have the Pelton wheel. Okay, so first you have this runner on which the blades are mounted. Okay, so you have a shaft here, then of course to fix this shaft we have this, or else we can make this a bit small also, no issue. Okay, so there is a shaft and ultimately there is keys and all to fix it. Okay, let's not write so much. So let's see. Don't draw till I finish. Okay. Fine. I'll stop here. Maybe some 8 blades you'll get. It's fine to visualize 8 blades. So I'm drawing the things. Look. Just a second. I'll draw one more circle so that the diagram looks little good. Okay. Okay. So let's observe certain things then. Fine. So okay. So you have the wheel like this. So these are the rivets to which you attach this. All the wheels are in same direction, no? Correct, na? All the wheels are in same direction, no? Okay, good. Okay, so you got the Pelton wheel. Okay, fine. Did you all like? Can you believe that this is a Pelton wheel? Okay, so this is the Pelton wheel. Now let's see. So this is the shaft. Let us now write the story that you have. Shaft. Okay, these are called buckets, and this is the runner, of course. These are called buckets. Okay, so this is the Pelton wheel, of course. Then let's see. You have a jet of water which is coming and hitting this. Okay. So let's say you have some nozzle in general. So let's say there is a reservoir, big reservoir. So there is a fluid reservoir in this. Then there's a penstock, the pipe which transfers fluid from reservoir to the turbine. Since this is not to the scale, I am breaking it because dimensional I should show that it's a length is something big. Okay, and then you see now this is connected to a nozzle ultimately. Okay, so this is a nozzle which you have. Compared to the size of the turbine, the nozzle size is less. This is called the penstock, and this is the reservoir. So what happens? This liquid will travel all the way and finally hit this. Okay, so this will hit this jet. And normally, depending upon the power requirement and all, we keep 2-3 nozzles also. It depends. Okay, we'll see what are the how many number of nozzles we have generally. Okay, for vertical shaft, for horizontal shaft. Sometimes it is mounted on a vertical shaft. Sometimes it is mounted on a horizontal shaft. There are a lot of things. So let's see if this is the Pelton wheel. Okay, and you have the buckets. Now to understand the transfer of mechanism, we should check the blade cross section. Okay, so how does a blade look like? That's it. Okay, so if you take a blade for example like this. So this is one blade. Okay, so this is a blade. If you look at the side section of the blade, how does it look like? So blade, if you look at a bucket, okay, the bucket, if you are seeing in this direction, it looks something like this. Look, how does it look like? You have the vertical line. You have a small cutting here on both the sides. Okay, then you have something like this. So this is the bucket actually here, the cross section of the bucket. Okay, and of course it is attached to the rivet and all. So this is how a bucket looks like. See, many of you might not understand this, but I'll show you a picture so that we can understand. Normally we have a lot of Pelton wheels. You can see this maybe. I hope you can see this image clearly. So these are a lot of buckets which are mounted on the wheel. At the same time, can you see there's a cut here, small cut. We'll see why that cut is there and all. But in general, if you can observe this clearly, I think you can see it's like a 2 half bowls like this. Okay, if you see the wheel is like in this shape, correct? Can you see the wheel is actually having like 2 half bowls actually like this, and it is intersecting and this point is coming up. That's what you have. Okay, so in general the wheel is something like this, so that the fluid, when you hit it, the fluid ideally hits somewhere here, it travels to the bowl and come up again, it comes out. Okay, so means whenever you hit a fluid jet here or at any point in general, the fluid hit here splits into 2 parts and it glides all the way along it and it comes out. Did you understand this? Yes or no? The fluid enters here, hits it, and then smoothly slides and comes back. Like in this diagram, you can see the fluid hits here, then it smoothly glides and comes outside actually. Okay, did you understand how the flow happens in this? Yes or no? Please type it in the chat box. Okay, can you understand this? So fluid hits here and comes out like this. So if you make a cut at this point and cross section, we'll see cross section of the bucket. cross section of the bucket. So what happens? I'm drawing the cross section. So if you pick one bucket and if you see it in the front view, this is how you see. Now if you make a cut at this point, it appears something like this. So this is how you have the bucket actually. Of course, it's symmetric. I think I'm not able to draw a very symmetric picture. I'm not a very good artist, but okay. So this is the cross section of the blade. So what happens? Fluid come in this way, hits it, gets splashed like this. Okay, and this is the blade, of course, bucket, cross section of the bucket. Now did you understand? So basically this diagram is like the side view of this. If you are looking from side, it appears something like the fluid is going in and coming out, which if you cut and see from the top view, it appears you can see the complete coming out. Okay, so this is what you. So let's see in reality what happens. This bucket actually moves in this direction. Okay, because let's say for example if you are impacting at this point, so this bucket, if you are in interest, so this bucket is actually moving in this direction u. When this bucket moves, because ultimately this is rotating at some speed n, so let's say n. Okay, so in such case ultimately this bucket moves with speed u. Now one thing that you can understand is I'm making one assumption here. Frankly speaking, when this, let's say for example if the jet is hitting, it's a normally the nozzle is big, it interacts with 2-3 jets simultaneously. Let's say for example if fluid interaction is like this, from the point of rotation from the center to here and to here, the distance is different. Yes or no? Means from this point to this point the distance is something different, the radius is different, and from this point to this point also the radius is different. Okay, so in reality if you take a bucket, water impacts that bucket at multiple points at different radius. Okay, but practically what we are taking for calculation purpose, we assume the complete jet is hitting at some mean diameter. Okay, so let's say this is Rm somewhere here, so this we call this as Rm. So this is Rm actually here, and Rm is equal to dm by 2, where this dm we take it as the mean wheel diameter. Okay, so dm is the mean wheel diameter, or it's also called as the peripheral diameter sometimes. Peripheral diameter. Okay, now try to get something. From this point you can understand fluid is going here, hitting and coming back. Okay, the variation in the diameter is along this line, correct? Can you understand? If this is this bucket, then somewhere here is the center of rotation. So from here to here and here to here there are a lot of distance differences. So can you please make a recorded FM available in this batch so that we can understand better the context of FM concepts? Fluid mechanics. Okay, I'll talk. Okay, just let me finish this because it's a nice concept. It will break again. So see here, if you have this point here, when you have multiple points like this, can you understand something? The diameter or the radius at which the fluid goes to the bucket, impacts it and comes out is same. Means during the course of interaction from inlet to outlet, the radius of the fluid where the fluid is impacting the bucket is not changing. Yes or no? Can you understand this? Like from this point, like let's say if liquid, if this you take as Rm for example, which means fluid when it goes here again comes out at the same radial location like this. Like in this case, as I have told you, if fluid is hitting at this point and let's say the radius from this point to this center hub is some distance, then the fluid which is impacting here is let's say coming out again to this point. Okay, so it goes smoothly and comes out like this. The radius of this and the radius of this is same, correct? Yes or no? means fluid inlet and outlet are at same radius. Can you understand this or not? Can you understand this or not? Please type in the chat box. Okay. So fluid inlet and exit are at the same radial locations. Yeah. Is this understandable? Why I'm taking? Because in the head delivered term, you have u1 square minus u2 square. I want to talk something about that. Okay. So let's see. Fluid inlet, or else I'll write it this point somewhere here. You can check. Fluid inlet, fluid entry and exit. And exit are at same radius. Okay. So fluid entry and exit are at same radius. Like for example, you see the fluid goes here, again comes back at the same radial location. Okay. Then let's see. Now let us try to analyze. So this bucket is actually moving at some speed u. So what I can do is maybe something like this here. Okay. So what you can understand is this bucket is actually moving in this direction with speed u, of course. Okay. So this bucket is moving in this direction with speed u. And fluid is also coming out at velocity u, of course, like this. Okay. Sorry, fluid is coming at velocity v, let's say, for example. So v is the velocity of this fluid which is impacting the jet, for example. So if this is v and this is u, ultimately what happens? The fluid particle, once it strikes it, it's going out in this direction, correct? In these directions. So here, if you observe something, the jet is getting deflected by some angle. Okay. So this angle by which the jet gets deflected, you can check something like this. Okay. So in fact, it's like tangential like this. Okay. Because that's the location where the fluid leaves, of course. So this angle is called the jet deflection angle. This angle is called theta, and theta is the jet deflection angle. And normally in Pelton wheel, it is maintained something like 160 and 180, somewhere in between 165 degrees to 170 or 170 degrees. Okay, beyond that it is risky again. Why? I'll tell you. This is theta. So this angle, whatever you have here, this is called as beta, which is like 180 minus theta, of course. Okay, so beta is basically 180 minus theta. That's it. Okay, so that's beta. Now when you observe something, let's say if this is the v and the fluid is coming with, ultimately fluid when it's interacted, it comes out with velocity vr2, let's say. Okay, so this is vr2 because it is symmetric. Is this clear to all of you till this point? Did you understand? Fluid goes like this, impacts and comes out smoothly, but all these 3 points are at the same radius. That's what. Okay. Please type in the chat box. Is this clear to all of you or not till this point? Chat box is not moving. Just a minute. Okay, charts are not there. So please confirm. Yes or no? Please type in the chat box. Is this clear to all of you or not? Everyone. Saifuddin, Asfaq, Prashant. I comment in the chat box now. Charts are not coming. Let us refresh the chat box then once. Yeah, it strikes only at the center. Okay, there are now comments, lot of comments. Okay, It strikes only at the center. That's what we are assuming now. It strikes all over the length of the blade. I mean, all over the length of the bucket. But we assume that it's hitting only at the center. Okay, because we neglect the radial variations. That's it. Okay. So let's see. This is 180 minus theta. Now, if you try to draw a velocity triangles, okay. If you try to draw a velocity triangle, this is the absolute velocity. So, out of which you have u velocity like this. Okay. So this is u velocity. So this is u, and this is v, of course. So ultimately, from here to here, it's the relative velocity. Okay. So this is vr1 actually here. So let's see. Let's denote this with blue color. This is u, and this is v, and the total is the absolute velocity like this. The total is the absolute velocity which you have. 1 maybe at inlet. Okay, so this is v1, because ultimately, you know, if you have absolute velocity, this, if you have some u and you have the relative velocity, then ultimately the absolute is given by the vector law of addition. You know, this we have seen already in the velocity triangles. Now let's see at the exit what happens. Let's say, for example, if you take this as the exit, or you can do top also, but top no space, so I'm doing the bottom one. This is something like VR2, correct? So this is VR2 actually. This is VR2, and you also have u here still in this direction. So this is u. So what would be the absolute velocity at this case? The absolute velocity at this case is going to be v2, something like this. Okay, so this is like v2. And what about this angle? If this angle is beta, then this angle is also beta, correct? Because this is the angle between the line and the horizontal. So similarly, if you extend this like this, this angle would have been beta. It's symmetric. Okay, so this is beta. So ultimately, if you resolve, this is v2. So if you resolve this, okay, so if you resolve this v2 absolute velocity, because you need tangential components and radial flow components, but it's okay. So let's resolve this using yellow color. Yeah. So if you resolve this, so you can clearly observe this small part, whatever we have, this is VW2 tangential component. Okay, and this is the axial, I mean the radial component, which is VF2, let's say. Okay, so this is the tangential, and the direction perpendicular tangent is the radial. So VF2 is what you have. So this is VF2, because the tangential and radial component should be always resolution of the absolute velocity vector. Okay, even in velocity triangles, in the last class I have shown you, when you are drawing tangential components and radial components, you should draw for the actual velocity, not the relative velocities. Okay, whatever is the actual velocity that is there, the absolute velocity, for that you have to draw the components. So here this V2 is the absolute velocity, so that's why I'm writing it as VW2, and this is VF2. Okay, so beta is the angle at which the jet is deflected. Is this velocity triangles clear to all of you? Here, of course, the velocity triangle is just a straight line, because all these things overlap. Clear? If you draw a velocity triangle here, same thing would have got reflected like this. Is the velocity triangles thing clear to all of you? If velocity triangles are clear, then we'll observe. Depending upon the geometry of the blade design, only the velocity triangles change. Once the velocity triangles, if you can spot, everything is same. Doing the analysis, trigonometry, all this is basic stuff. Okay. So please type in the chat box. Is this clear? V2. V2 is the absolute velocity at the exit. Okay. V2 is the absolute velocity, because if you have L2 and the blade is also moving, then the fluid would have come out with some absolute velocity, na, obviously. Okay. Fine. So let's see. Then let us name these points, maybe like A, B, C, D, E, F, G, for example, because we need some names to do some mathematical analysis. Okay, so now this is a triangle, very clear. Ultimately, if you take V component, the total is VW1. This total here is VW1, because purely the velocity itself is in the tangential direction. That's what I call this is a tangential flow impulse machine, because the fluid is just, you can see this is the machine and the fluid is exactly going as a tangent. So at the inlet, definitely the complete velocity is in the tangential. That's what you will understand from this also. Okay, so now let us do some mathematical analysis. So first, power developed by the turbine. In fact, if there is no mechanical efficiency and all, so power developed by the turbine is equal to rho g q into h. Correct? This is the power, because this is the head supplied and this is the weight, which is head supplied is nothing but power delivered to the water per unit weight. So you have to multiply that with weight, of course. Okay, rho g q h is what you have. So this is power delivered by the turbine. Correct? This is the head delivered, means head is nothing but power delivered for 1 unit weight of the fluid. So if you want the total power developed by the turbine, you have to multiply this head with the weight of the fluid. So O into Q gives mass flow rate into G, that is power. Okay, energy per unit time. So rho g q h. Now let us see. Rho g q is fine. Rho g q is fine actually here. So what can I write about this h? It is like VW2 U2 minus VW1. Sorry, developed by the water. It's okay. So VW1 U1. Okay, yeah, it is like VW1 U1 U1 minus VW2 U2 divided by G actually here. Okay, so this is the expression we have. With this we have generated from the Euler's equation. Head delivered to the turbine is VW1 U1. 1 is inlet, basically 2 is outlet. So this is what we have. But in this case, since R at inlet is same as radius at the outlet of the flow, because the fluid is going in at the radius and coming out at the same radius, if you multiply omega on both sides, correct? So this is what you have. So let's say this is U. This is U, of course. So let's see. Therefore, P is equal to rho Q, G and G gets cancelled, of course. Okay, so G and G gets cancelled. So rho Q times of VW1. So what is VW1 from this triangle? So let's see. VW1 is nothing but the total length. Okay, and what is the total length? VR1 plus U, which is V1, of course. Okay, so we can write this as VR1 plus U. Okay, so VR1 plus U into U1 is also U minus VW2. So what is VW2? VW2 is basically this length FG, correct? So you can see VW2 is equal to FG actually here, right? What is the length of FG? FG can be written as this. FG can be written as, you don't know this angle, but you know this angle. So what we can do, FG can be written as EG minus EF. EG minus EF is what you can do. Okay, so what is EG? EG is this complete length, which is VR2 cos beta 2 minus U actually here. Okay, because EF is U, that's it. Okay, so this EF is U, that's what. So VW2 is VR2 cos beta 2, because we have to do something in terms of known quantities actually. Okay, so let's say this is VR2 cos beta 2. Of course we don't know what is VR2, but we can calculate. I'll show you. VR2 cos beta 2. So let us substitute here. But before substituting, you have to tell me one thing. This VW2, the direction, if you check this VW2 direction, this VW2 is positive or negative? It's towards the positive direction of the motion of the blade or negative side? Please tell me. This VW2 is positive or negative in this case? Come on, please type it in the chat box. Negative, right? So it becomes minus of VR2 cos beta minus U into U, of course. Okay, so this whole quantity, that's what you have. Okay, so this is something that we have here. So if you make simplification, the power developed by the turbine is rho Q into VR1 plus U minus of minus plus VR2 cos beta minus U times U. One more U is there. Okay, that U is also there, because this U and U from the two terms at the multiplication I am taking out as common. Then ultimately this plus U and this plus U and minus U gets cancelled. So we can write this as rho Q into VR1 plus VR2 cos beta times U, of course. So what one can do here is, we can take VR1 constant, because practically speaking the relative velocity should remain same throughout the plate. Like normally in case of impact of jets and all, we have seen normally if the inlet if this is the plate, for example, if the fluid is going inside the control volume at V minus U velocity, that's the relative velocity, of course. Okay, so V minus U stayed V minus U all over the plate, correct? Because there is no friction along this plate. Okay, but in reality, when even though you make the buckets blades smooth, there is always some friction. So VR2 will be slightly reduced because there is a loss due to the friction. Okay, so in general, this VR2 by VR1, we define K is equal to VR2 by VR1, which is the velocity reduction coefficient. Velocity reduction coefficient. Okay, so this is the velocity reduction coefficient, and K is approximately equal to 0.98 of that range in general. Okay, so did you understand? Normally in case of flat plate, what happened? If fluid is entering with, if this plate is moving, fluid is also coming like this. Okay, so V minus U is the relative velocity at which fluid is entering the control volume. This V minus U remained V minus U until all the exit. Okay, but in reality, what happens? During the passage, there could be some friction, because of which there is a loss in kinetic energy. Okay, because obviously there is no pressure energy, so there is a kinetic energy loss little bit. So that is K 0.98. So therefore, this power P can be written as rho Q. If you take VR1 constant, you have 1 plus VR2. If you take VR1 constant, you have a denominator VR1 here. So VR2 by VR1 is constant, this velocity reduction coefficient, K cos beta rho Q VR1 into 1 plus K cos beta into U, of course. This is the velocity. But what is VR1? You don't know VR1. Okay, K you know, depending on the machine. Let's say if the machine is in significant service for some time, then ultimately you can tell K is 0.98, 0.97 and all. Beta is known to you. Density of the fluid, discharge, you know, you have flow meters. But what is the velocity VR1? Since you don't know directly, you can obtain from this. So can I say from this, VR1 is equal to V1 minus U? Yes or no? Simple velocity triangle, and of course it's a straight line here, just a length. So VR1 can be written as V1 minus U from this triangle. So therefore, the power developed by the turbine is given by rho Q into 1 plus K cos beta into V1 minus U times U. Now you know everything, because you can look at the rotational speed of the, if you have a tachometer, you can measure the rotational speed of this Pelton wheel, because U is equal to, you know what is U? U is equal to pi dn by 60. You know this. Okay, because if you know n, you know the mean diameter. If you take, then you can calculate what is U. U is known. Velocity of the jet to the nozzle can be figured out. K is known to you. Beta design is known to you. Density and discharge are also known to you. So you can calculate what is the power developed by the Pelton wheel actually. Did you understand? See, the only thing is, principles are same, but depending upon the shape of the blade, location of the entry of the fluid, exit of the fluid, these velocity triangles will change. That's it. Okay. Depending on these velocity triangles, these calculations will change, but the fundamentals what you apply is same. Clear to all of you? Did you understand? This is the formula for this power developed by the turbine actually of a Pelton wheel. OQ 1 plus, you might have seen this in many in your semester exams. Faculty might have derived this for you in college and all, but generally I have seen people don't use this. They use some you know, they'll tell you that this formula comes up somehow, they don't know, and they'll start applying the terms, and many people don't have this clarity on this minus sign. Why can't we take VW1 equal to V1 directly? Because VW1 is V1 only, no? Yeah, VW1 is V1. See, I have modified VR1, not V1, VW1. VW1 is V1, of course. You can take directly V1, okay? But again, I want to take the effect of this K, that's why I have got it. If you take V1 as VW1 as V1 directly, and if you substitute, then what happens? This is V1 all over. Then this minus U will be left inside, okay? So then the calculation is like little hectic, and it's not very comfortable to look at. That's the reason, nothing other than that. Okay, is this clear? Did you understand how we have done this power calculation for this Pelton wheel? Yes or no, something? No. Okay, yes. Are you all understanding how did I get this calculation? OQ 1 plus cos theta, K cos theta into V1 minus U into U, of course. Okay. Now let us calculate what is the hydraulic efficiency of this Pelton wheel. Okay, so you have got the Pelton wheel, of course. So this is the Pelton wheel, of course, here. So what's the hydraulic efficiency of this Pelton wheel? Let us check it. Okay, so hydraulic efficiency of the Pelton wheel, or sometimes it's also called as the wheel efficiency, because it's just a wheel, so it's also called as the wheel efficiency. So let's see. We know one thing. Hydraulic efficiency is power delivered to the water, which is nothing but the power produced by the water if there is no losses and all. So power delivered to the water by power delivered to the water by energy available at water inlet, or power available, because we are dealing in terms of power. So power available at rotor inlet. Okay, so at rotor inlet, this is what you have. Now if this is the power available at rotor inlet, now this is an impulse machine. Okay, the complete power which is available is only available in form of kinetic energy. You know, there is no pressure energy. So therefore, can I write this as can I write it this way? Because the available energy at the water inlet is nothing but this kinetic energy of this jet. Apart from this kinetic energy of this jet, nothing is available. So if you know the mass flow rate is m dot, then per 1 second the kinetic energy that's flowing into the Pelton wheel is half m v1 square by time. So half m dot v1 square, of course. Okay, so that's what you have. Then if you simplify this, let's see, this OQ and OQ gets cancelled. So this is something like 2 times. Okay, so 2 times this 2 is here, 1 plus k cos beta into, try to observe something carefully, this v1 square I am adjusting here as 1 minus u by v1 into u by v1. Can I do it this way? Yes or no? So this is the hydraulic efficiency. Now one thing, first of all, for the same flow rate you can control the velocity, correct? At the same time you can also control the rotational speed of the Pelton wheel by governing. Okay, we'll see governing again later. So 1 minus u by v1 into u by v1. Now out of these things, 2 is constant, this 1 plus k cos beta is also constant, but u and v1 can be fluctuated and they can be changed, and obviously anyone wants the hydraulic efficiency to be maximum, correct? So what would be the condition for the maximum hydraulic efficiency? Let us calculate. For maximum hydraulic efficiency, a maximum hydraulic efficiency. Okay, so for maximum hydraulic efficiency, ultimately one thing that you should do is, by what is the variable here, u by v1, this should be equal to 0 actually, correct? So if the machine's hydraulic efficiency has to be maximum, the only variable in this equation, in this expression, is this u by v1. So the first derivative with respect to that will be, this should be 0, of course. Okay, so if you do that, this implies d by du by v of this quantity 2 into 1 plus k cos beta into 1 minus u by v1 into u by v1 is equal to 0. Now ultimately these fellows are constants, you have nothing to do with this, they are just constant, take out and on the right hand side. Now the differentiation of this gives you first function into derivative of this with respect to same thing. Derivative of this with respect to same thing is 1 plus u by v1 into derivative of this with respect to u by v1 is minus 1. So this implies 1 minus 2u by v1 is equal to 0. So u by v1 should be equal to 1 by 2. So this ratio is actually important. For a Pelton wheel to have the maximum wheel efficiency, the rotational speed, or the basically the peripheral speed of the bucket, should be half of the jet velocity. This is a very important conclusion. Many times in GATE they have asked this. Okay, so u by v1 is equal to 1 by 2, of course. So therefore, for maximum, of course, if you want the condition for maximum, you can calculate the second derivative and put u by v equal to 1 by 2. You will get negative. Okay, so for eta h max of Pelton wheel, this u by v1 is equal to 1 by 2. Okay, so this is one condition, simple bit of maths that we can work out. First derivative equal to 0. So therefore, for the Pelton wheel to operate at maximum velocity, to operate at maximum hydraulic efficiency, at maximum hydraulic efficiency, bucket peripheral velocity, or bucket peripheral velocity should be equal to half of the jet velocity. This is a very important conclusion that you can get on this. Okay, and then obviously once you know the condition, what would be the maximum hydraulic efficiency? Therefore, eta h max is equal to 2 times of 1 plus k cos beta into 1 minus of u by v1, but u by v1 is 1 by 2. So 1 minus 1 by 2 is 1 by 2 into 1 by 2. So then ultimately these two things cancel up, and you have eta h max is equal to 1 plus k cos beta by 2. And normally if k is 1, generally if they don't tell you any friction and if they don't give you k, it's like 1 plus cos beta by 2 directly. Okay, that's all. So these things you might have learnt in some different way, but you can see the constitutive logic behind building all these things. Okay, so 1 plus k cos beta by 2. In reality, what happens is, in reality, you will observe that the hydraulic efficiency is not maximum exactly at 0.56, but slightly around 0.46. Okay, in reality, the reason is friction. All these things place the picture. Okay, so it happens at around u by v equal to 0.47, 0.46 of that range. That 0.03 variation is due to the presence of friction of the liquid. All these things, of course. Okay, so some nice things about the Pelton wheel is, of course, so it generates power. So it works under high head. Actually here. Why it's a high head is because if you apply Bernoulli's equation between this point and this point, both are open to atmosphere, same pressure, nothing. Okay, yeah, reality. So this is, if you apply Bernoulli's equation, the velocity at which it comes up, v, because that's the prime source of energy conversion. Okay, so for this velocity to be high, v is in general v1, whatever we call, this is root 2gh ultimately, and sometimes it's also multiplied with the coefficient of velocity. You might have seen in this devices like piezometers, venturimeters, or in fluid mechanics CMS I might have taught you. So v1 is equal to cv root 2gh. This cv here is called coefficient of velocity. Okay, and if the impact has to be powerful, ultimately for this v has to be high, and for v to be high, this h has to be high. Okay, so it operates under high speeds actually. Okay, and compared to Kaplan and Francis machines, this machine is generally of low speed. Okay, it's because of the pure impact where pressure energy do not. Just a second, guys. I think some important call they have been calling multiple times, but it's okay. I'll talk to them after the class. Chalo. Fine. So what we are talking, yeah, coefficient of velocity. So the high head should be very high. At the same time, compared to the Francis harness and Kaplan harness, this machine operates at low speed generally, comparatively. Okay, that's why because of low speed, the protection equipment around the machine is also a little low, to be frank. So this operates at under high head and low speed. Normally, if you look at the specific speeds for these machines, NST for Pelton is something like 8 or 10 to let's say for example 25 per single jet, and 25 to around 30, 32 something. It's not very clear distinction. So 31 for 2 jets. Okay, so this is the specific speed, which is generally low in general. But normally if you take Francis Harness, the specific speeds are around of order 100, 200 of that range. Okay, Kaplan is like beyond, like more than 200, like 500, 400, 600 at very high speeds. This Kaplan operates, but normally in this case, the specific speed values, if you look, this is the typical range at which they operate. Okay, also, so it works under high head and of course low speed. So this is a bit important point if someone asks you. And the mass flow rate also is very high generally. Okay. Then no, I mean mass flow rate is high, but not as high as Kaplan turbines and all. They're much higher. In case of axial flow machines, the mass flow is like drastically high. Okay, so generally these are the things, some nice points I thought of talking about. Also, normally if you have the jets, okay, so for horizontal shaft, normally in some SSCJE or something, if these things come up, they'll ask you. But in general, GATE and ESC, they don't ask these kinds of stuff. They give you some calculations like this. So for vertical shaft machine, they look something like they look something like, for vertical shaft, they look something like 4 to 6 jets. Yeah, 4 to 6 jets is what we have here. Okay, so these are some nice salient points about the Pelton wheel, of course, which you can calculate. Clear to all of you? So basically we have seen the power calculation of this Pelton wheel. So it's like almost some 5 beautiful slides we had, the first slide being more beautiful. So this is the Pelton wheel, of course. So if that's the Pelton wheel, then we had this penstock. Basically penstock is the line which connects the reservoir to the inlet of the turbine, of course. So it's normally called the penstock, and it's a nozzle for faster impact with high velocity, because we want to increase the velocity, because the kinetic energy is the only energy which is available. So we want to increase the kinetic energy as much as possible for a given flow rate. So this is how it happens. Okay, did you all understand details about the Pelton wheel? Yes or no? Did you understand why I have taken pain in deriving this term? H is this. Okay, now I hope you can connect. Why I taught you about the velocity triangles? Because of this. Why I have derived the Euler's equation? Because of this. Then differentiation and all, basically simple things. Okay, so now let us look at the Francis runner. Okay, so what are the important things of a Francis wheel? Actually, we'll see, and we'll also perform the hydraulic efficiency analysis for the Francis wheel as well. Okay, it's been 3 hours already, and I think it's going good. Okay, let's finish Francis. Okay, so Kaplan and pumps will start in the next lectures in detail. Okay, so let us finish Francis also. Okay, some 15-20 minutes, that's it. Okay, I don't take more time. It took around some half an hour. So next, similarly Francis will also 20 minutes. Okay, but I'll draw some nice diagram again. Okay, so this is the type of the machine that you have: impulse tangential flow impulse machine, because you see it's an impulse purely, and it's tangential, the flow is purely tangential to this wheel. Okay, that's all. Now let's see, let us look at the Francis turbine, or the Francis runner it's called generally. Francis runner. Okay, so let's see, it's basically a radial flow, a reaction machine, Okay, so radial flow reaction machine, of course, and obviously it's the name itself tells you the flow is the bulk flow is in the radial direction. Okay, it moves along the radius, but of course it has got tangential components. Okay, it's not like the flow is radial means that has only radial component of velocity. The bulk motion of the flow is in radial direction, but it can have tangential components as well. Okay, so let's see first the important components of the main components of a Francis turbine. A Francis turbine. First, we have the runner, the blades mounted on it. We have the guide vanes or the stator. It's also called as the stator, basically. And then we have the most important component like spiral volute casing. I've seen a Francis runner many times actually. Okay, and it has also got the draft tube, which is very important thing again to look at. So draft tube, these are the things that you have majorly. Okay, you have a lot of auxiliary components and all, but still these are the main things which make the turbine operate at least. Okay, so generally speaking, this Francis runner has a specific speeds of is around some 31 or 51, sometimes around 45 to something like 230 of that range. It's a very wide range of operation. Okay, and also it is operated at low heads because the pressure energy will be pushing the fluid so much. So low heads and high velocities, of course, or medium velocity compared to Francis, I mean compared to Kaplan, and high speeds generally. Okay, because in this case the main reason for the impact is not the pure velocity, the pressure energy is also there, because as you can see it's a reaction machine. So in case of reaction, the pressure energy will push the flow onto the blade, so ultimately the wheel rotates. Okay, have you seen Francis turbine in your college, in lab somewhere? Yes, no? No, you haven't seen a Francis runner. No, seriously. BTech is finished or not? How many of you are college going? How many of you have already finished this fluid mechanics lab or hydraulic machines lab? No. How many of you have already finished this lab, hydraulic machines lab? 2 years back you finished. 2 years back in our college. Okay. Deepthi, Upadeep, you haven't seen seriously Francis turbine? Pass out. Okay. Chalo. I have seen, and when I was working with HPCL also, there's a chance that I got to see this Francis turbine. Okay. Anyway, let's see. I'll show you a Francis runner. First of all, I'll draw something, and then I'll make you understand this. So normally, you have the shaft. First of all, you have the turbine. This is the turbine, for example, let's say. Okay. Fine. So we have the turbines, and of course there are blades which you can see maybe like this. I'm spotting only few blades because the others are not clearly visible. Okay, the fluid entry into this, it goes radially because you know this is the radius, so it's coming radially in this direction, and ultimately the fluid drops up, something like this. Okay, So this is the turbine, and this is mounted to the shaft, of course, to a generator shaft. Which color shall I take? White, blue, green, yellow, green. Okay. So this is the shaft on which it is mounted. Okay. So this is the shaft on which it is mounted actually. And this shaft will be connected to the generator shaft, and this rotates about this shaft. Okay. So this is a wheel which rotates. So if you write the bit of nomenclature here, so this is the turbine ultimately, and this is the casing. I mean the turbine is somewhere just inside. So casing, this tube is called the draft tube. We'll see what is the purpose of this draft tube and all. Then this is the shaft and blades. Okay. So this is a simple construction. Now let us have some bit of idea on the turbine part. Okay. So this is what the turbine you're seeing, and the fluid is coming almost radially. Okay. Because if this is the center, then this is the radial direction. So the flow is radially inward because it's a turbine. NT would be at a higher radius compared. Okay. So in the Telegram channel, please charts. Okay. So please chat in the chat box if you have a doubt. I mean, chat in the Telegram channel. Okay. Fine. We'll continue the lecture. We'll finish this Francis wheel, and because we have anyhow started, so we'll finish this Francis wheel and we'll make a move. But meanwhile, if you have doubts, because I'm not able to see the chat box actually, I don't know what happened. So just communicate in the Telegram channel. Okay. Yeah. Okay. So this is the Francis runner, of course. So if you look at the runner, okay. So let's see how does it look like. So let's see. You have this runner, of course, and surrounding this runner you have guide vanes, of course. Okay. So you have the guide vanes actually in this case. So how does this guide vanes look? We'll see, of course. So these are the guide vanes, and you have the shaft at the center ultimately. So you have the shaft and also a bit of casings as well. So let's see this. So you have the shaft, and let us see. Okay, so it's fine. So let us see. So this is the runner actually here. Okay. So this is the okay. We'll do the nomenclature later. First, let us write the diagrams. So these are the stator vanes. So these are the stator vanes, of course. Okay. So which guides the fluid into this. Fine. So these are the stator vanes, and of course this orientation of this stator vanes can be modified. Now you have a casing which is the spiral casing, of course. So what it does is, like, you can observe something like so. This is a spiral casing actually. Fine. Okay. So this is the spiral casing. As you can see, it's like a spiral, of course. Okay, it's like a spiral. Fine. So yeah, it's like a spiral. So if you connect this, so it's like a spiral casing almost. So let's write this is a spiral casing. Then this is the rotor, and these are the rotor blades actually. So maybe something like this are the rotor blades which you can see it, and these are the stator vanes. You also have the guide blades actually, okay, in fact. So you can check, like there are something like this guide blades, of course. So you have the guide vanes as well, okay. So I hope it's clear to all of you, because I was not able to see the chat box, okay. So then in this case, what happens is the fluid comes into the picture like this. Along with entering into the veins, it also travels like this. Okay, so you can see the fluid, when it's traveling, it also enters. Now why the casing is spiral? This is the first question that anyone can have, okay. So why the casing is spiral? Let's see. Why casing is spiral? Anyone answer? Can someone answer why the casing is spiral? It would have been a uniform, nice cross section, right? Why the casing is spiral actually? Come on, in the Telegram chat. Any one of you? Why the casing is spiral? Any idea why this casing has to be spiral? Anything to say? Why the spiral is casing? So because in general what happens, see, when the fluid is here, there is a high amount of flow available to enter between these two guides, correct? So between these two guides, the amount of fluid available to go in is high. But for the same gap here, compared to the amount of fluid here, the amount of fluid here is available is less, okay? And as the discharge is decreasing in this peripheral direction, because at every junction the fluid is just flowing inside, so when the fluid is flowing inside at each and every part, then the amount of discharge along this periphery will keep decreasing, okay. So when the discharge is decreasing, the fluid finds it difficult to enter in this direction. So ultimately what happens, we decrease the casing so that the area of cross section of the flow decreases. If area of cross section of the flow decreases, the fluid moves with high velocity, okay. So that's the reason for the casing to be spiral, okay, to concentrate the flow, yeah, of course, okay. So basically to make the flow area less so that the velocity increases and the fluid just enters it, okay. So this is the casing, of course, the spiral casing again here. So you see, it's not actually in contact, of course, so it's something like this, okay. So something like this. Then if this is the casing, so I hope you all can see the Francis runner now in this case. So this is the runner basically. Now if you take this runner alone, okay, so try to understand what I'm telling you. So if you take this as a runner, for example, if you have this as, oh sorry, if you have this as the runner, for example, with a shaft at the center, okay, so this is the shaft, then what happens if you take the blades, okay. So if you take a blades, for example, the blades are something like this in general. So maybe I'll draw it in the next page so that you can get it in a much better idea. So but is this clear to all of you till this point? Now these are the different nomenclatures, and the fluid actually enters radially. You can see the fluid is entering to the runner radially at all the points, okay. So the fluid is coming radially, almost radially at all the points, and because of the inclination on the blades, the impact with the blades will actually rotate this runner, of course, okay. So let's see, if you have this runner, okay, so let's say if this is the runner of the Francis wheel, for example, okay. Fine, so this is the runner. Now you can observe, or else I'll draw it a little, oh sorry, fine, okay. So if this is the runner actually here, and if you have the shaft something like this, I'm trying to draw a 3D view so that you can understand here. Now let us see if this is the shaft location, and this is the runner actually in this case. Okay, now if you take the blades are something like this. So this is the blade actually here, one blade. Okay, so I hope you can see this, you can recognize this or not. So this is the blade, and coming here, so if you take between two blades, let's see what happens. I hope you can recognize that these are two blades. Okay, normally you have a lot of blades on this runner, so there are two blades like this which I am taking. Okay, so these are the blades. Similarly, you have multiple blades at each and every location of the periphery like this. Okay, so these are two are blades. Then this height of this blade, okay, and this height is different. Okay, and this is some gap, of course. Okay, so let's call this height as B1 and let's call this height as B2, which is nothing but the width of the blade is called. Okay, it's called the width of the blade. Okay, I think it's clear in the Telegram channel. Okay, so I hope it's fine to all of you. Okay, so then in such case, if these two are the blades, what happens? Fluid will actually enter into this in this direction and it will move out in the downward direction. Okay, now if you observe something, this height of the blade is B1 and if this height of the blade is B2, the velocity in this direction is the radial direction purely, correct? So Vf is the radial component of velocity. Radial component of velocity. Okay, so these two are blades, of course, and the fluid is flowing in this direction. So the radial component of velocity at inlet is Vf1 is equal to, let's say for the total 360 degrees, if you draw blades at all the 360 degrees, the discharge entering the turbine is Q. Can I write this as Q by pi d? If this is D1, let's say for example, so at D1 and B1, and Vf at exit is the same discharge divided by pi times. So let's say at the discharge you have the small diameter, because at the inlet the diameter is large, at the exit the diameter is small actually. So pi d2 b2. So this is the radial velocity, or sometimes it's also called as flow velocity, because that's the flow that's happening in this radial machine. So flow velocity or the radial component of velocity actually. So like this, you have blades at all the 360 degrees. Ultimately I have taken two blades to make you understand the flow actually here. Okay, is this clear? So please confirm in the Telegram channel once quickly. Is this clear to all of you? Everyone, please type it in the chat box. Let me try if comments, I can see the comments actually here. Yeah, still I'm not able to see the charts maybe. Okay, fine. Let's communicate in the Telegram channel then. Okay, so it's not there, right? So then this is V, velocity of the flow at the inlet, and this is the velocity of the flow at the outlet, of course. Okay, so then let us take a blade and let us try to draw the velocity triangles for this. Okay, so we have the blade, of course, and let us try to write the velocity triangles. First of all, before doing that, H is equal to Vw1 u1 minus Vw2 u2 by G. Okay, and you know, basically this contribution from the pressure side as well. This Vw2, this term is positive obviously, because if you look at the vane angle, something like this, or maybe like if you look at the vane, so you have some inlet, outlets and all. So can you observe something? This is a positive term. This term is greater than or equal to 0 generally. Okay, in this construction of the Francis wheel, the wheel cannot be bent backward, because ultimately it's like twisting the blade and breaking the blade. But in general, if you have Vw2, see basically this portion you cannot twist it again back. Okay, so like let's say if the flow is going like this, you cannot make it, like in case of Pelton wheel, what happened, the fluid has entered and it came out, right? But here what happened, this fluid, there is no chance that the fluid can actually reverse. Okay, it should definitely go into this and fall into the draft tube. Okay, why? Because if you try to bend this blade, then this flow will be obstructing the upcoming flow in the other directions. Correct? Got it? Let's say if you try to bend this blade, normally the blade is like this. Okay, if you try to bend this blade, the fluid, instead of going here, it will turn this side and will try to obstruct the flow coming from the neighboring blades actually. Okay, so one thing is you cannot reverse the blade and make sure this VW2 becomes negative of negative and it adds up to form more head. You cannot do that in this case. Okay, so the maximum thing you can do is this VW2 is greater than or equal to 0. So since this is a positive term and this is head, this term has to be subtracted. For maximum head delivered, for maximum possible head delivered, possible head to be delivered, what can I make this VW2? I cannot make this negative, okay, because I cannot bend this blade leftward. Design constraints are there. Okay, then what is the maximum thing you can do for this value of VW2 so that the head delivered is maximum? Tell me in the Telegram channel. This being positive is a loss for us, correct? Because it has to be subtracted from this first term. So it can be made equal to 0 or it can be positive. So what could be this value of VW2? It should be 0, correct? So this VW2 can be made 0. That's the maximum thing you can do to get the maximum head, possible head, of course. Chart play update हो गई है. अच्छा ठीक है, एक बार refresh करके देखेंगे. No, I can still see the same messages, but let's refresh, reload. No, still the same comments are coming for me. Okay, so this VW2 is 0. So if VW2 is 0, what does this mean purely? This implies tangential component of velocity at exit is 0. This implies flow at exit is purely radial. Flow at exit is purely radial, correct? If tangential component is 0, then ultimately the flow has to go out radially. Okay, so here when it's entering, the bulk motion is in radial direction, but it has got some tangential components. But for this H to be maximum as possible, this fellow should go purely radially at the exit. Okay, that's why if you check the diagram in which I have drawn, maybe you might not have observed a bit, but you can check here. I have drawn this to be purely in radial. Okay, I think I have to slightly bend these diagrams, but normally the flow is like purely radial actually. Flow at the exit of the Francis runner should be purely radial because of that issue. Got it? So this statement is very important statement, and fine. So the flow at exit is purely radial. So how do we design a blade if the flow has to be purely radial? Okay, so let us see. If you have a blade like this in general, fine. So let's see. This blade is moving with a velocity u, let's say. Ultimately the blade has to move because the runner is rotating. So this blade is rotating with a velocity u, of course, here. Okay, so that's u. Then let us see. Some fluid is trying to come in with velocity v in or v1, let's say, and the blade is moving in this direction. So this is velocity u for the blade. Then ultimately you get the relative velocity is vr1. This is vr1, of course. Okay, so this is something like vr1. Maybe I'll draw a big blade so that you can understand these things little nicely. Okay, so I think you can check it up now. So this is the velocity of the blade. Okay, so something like this. So this is VR1, V1, U1, VR1 in this case, okay. And ultimately if you resolve this V, absolute velocity into tangential and radial components, you know, this V1 I'm resolving, so you can see now this is the total VW1 and this is VF1, okay, the flow component of velocities, of course, okay. And let's call this angles to be something like maybe say theta, and this is phi, of course, okay. So theta and phi, for example. Then let's call this to be alpha, for example, alpha, and this is theta, okay. So let's make this theta generally, because some, it's okay, you can take anything, it's just some for some trigonometry, nothing other than it. So alpha is the absolute angle of the fluid at inlet and theta is the angle of the relative velocity, it's a guide, okay. Then at the exit what happens, look, so this is VR2, VR2, okay, and the velocity of the U is something like this, so this is U2, and the blade do not move with uniform velocity, sorry, this just the blade moves in this direction. So if this is the absolute velocity, so this is V2 in the closing direction, so this is V2 absolute, okay. So you can see if you resolve this VW2, this is exactly equal to VF2, that's all. There is no VW1, I mean VW2, because we want the blade to be VW2 is equal to 0. So whatever the exit that's coming up, it's the absolute exit should be in the radial direction 100%, okay. So that is VF2. This is the construction. Is this clear to all of you? Please type in the telegram. Did you understand this? This V2 is exactly in the radial direction, in the exactly upward direction, so that the VW2 component is 0 in this case, okay. Clear to all of you? Everyone, Shubhadeep, Asif, Nitish, Milan, Swati, every one of you, okay. So clear? So this component is such that it's exactly 0. Now let's see, and this angle is, let's say phi, for example, phi, okay. Any angles you can just denote. Now let's see, you call this to be A, again some nomenclature we'll put to do some analysis. A, B, C, D, okay, then E, F, G, of course. This point is very important, okay. Flow at exit is purely radial. They'll ask you why. That's the reason, okay. So let's see head delivered, because if you multiply with OQG you will get the same thing. So head delivered is equal to, okay, so head delivered is equal to, let's see if head is delivered, then in such case we have VW1 U1 by G, that's all, okay, because VW2 is 0. So since VW2 is 0 actually in this case, okay, so VW1 U1 by G. So what is VW1 directly? Let's try to get from these triangles. 1 by G times, okay, so VW1, of course. So let's write it in terms of V1, this, or else VF1. Let's write it in terms of VF1, it's okay. So VW1 is this complete expression. So VW1 can be written as V1 cos alpha, V1 cos alpha, okay. So V1 cos alpha is VW1 into U1. So what about U? U is this component, which is VW1 minus this fellow CD, VW1 minus CD. So CD is what we can write as of now. So this is 1 by G into V1 cos alpha into VW1 is again one more V1 cos alpha minus CD. So what about CD? CD can be written as VF1 tan theta 1, correct, because tan theta 1 is VF1 by CD. So tan theta is VF1 by CD. So this is something like VF1 by tan theta, or VF1 cot theta is what you can say, VF1 cot theta. cot theta. Okay, so this v1 cos alpha multiplied to this complete thing. Now what about v1? V1 can also be modified as in terms of v of 1. So sine alpha is v of 1 by v1. So sine alpha, so we have sine alpha is equal to vf1 by, so vf1 divided by vf1 divided by sine alpha is vf1 divided by v1. So v1 can be written as vf1 by sine alpha or vf1 cosecant alpha. Just a bit of trigonometry, so you have to figure out the things, that's all. Okay, so if you replace here, h is equal to okay, so h is equal to 1 by g times of v1 can be written as vf1 cosecant alpha. So vf1 cosecant alpha into, if you replace v1 with again vf1 cosecant alpha into cos alpha is also there, sorry. Okay, so see carefully, v1 is vf1 cosecant alpha into cos alpha is cot alpha, correct? Because cosecant into cos is cos by sine, so cot alpha. So this can be written as vf1 cot alpha times, similarly vf1 cot alpha minus vf1 cot theta, of course. Okay, so this is what you have, of course, here. So ultimately then if you take out this cot square alpha out common, we have vf1 square, vf1 square, okay, then cot alpha, cot square alpha. So if you take this as cot square alpha by g into, so by g into, so vf1 square cot square alpha into g, so 1 minus vf1 and vf1 gets cancelled, so cot alpha by cot theta by cot alpha. So this is the expression for the head delivered in this case. Okay, and this is already the best possible because we have already made vw2 to 0 and we made the blade exit to be purely radial actually in this case. Okay, so this is how we can get the expression, and normally if theta is given and alpha is also given, we can calculate the values. Okay, if theta is not given, see basically it's like some values of these are given, some values are not given. It's based on purely trigonometry, that's it. Okay, once you, the main job is to write these triangles. Once you know the triangles, by applying trigonometry and all, you can do the things. Okay, now this vf1 can be written in terms of discharge using q by pi d b1 or q by pi d d2, all these things. Okay, width of the blades, everything can be calculated using this this expression basically. Okay, using these two expressions, if you can figure out what is vf1, vf1 can again be calculated using trigonometry. Of course v1 is known, alpha is known, so sine alpha 1 you can do. Okay, also one more thing is you can also relate that phi. Okay, how come? This vr1 can be replaced with vr2. Okay, because if you want to bring in u2 into the picture, you can relate this vr1 equal to vr2. So whatever the expressions you have for vr1 here, you can replace with vr2 expressions. Like for example, vf2 cos phi is like or else vr2 sin phi is vf2. Okay, so vf2 is equal to vr2 cosecant phi. So you can relate the things again. Okay, so basically using all these things we can calculate. That's all. Now we'll have a discussion on the draft tube. Why draft tube is there? Okay, so let's see why draft tube is there. So let's see, because this itself is enough to achieve power, correct? Fluid will go impact the blades, then ultimately one hour will rotate and power gets generated. But how draft tube actually helps us? Look, this is normally called as tail race. Okay, so this is normally called as the tail race actually here. Okay, so that's called the tail race actually. Now here the pressure is atmospheric pressure. Here the pressure is atmospheric pressure. So normally you cannot bring the fluid to very low pressure because there is a issue of cavitation, you know this. Okay, but because of this, what happens? It's an expanding tube. So if this is expanding, then ultimately because of the continuity, we are dealing with liquids, the velocity of the flow decreases along this direction because the tube is expanding. Understood? So since the tube is expanding, area of the flow increases and velocity of the flow keeps decreasing here. So if velocity of the flow is decreasing, what happens to pressure? Come on, please type it in the chat box. Draft tube is to increase pressure at the bottom. Yeah, of course, I'll tell you. So that's what So practically what it happens is, look, at this case, okay, I'll draw the draft tube once again here. So see, there are types in this again, of course. So this is the tailless. Okay, so this point 1, let's call this to be 1. Then this point is exit to turbine or entry to draft tube, basically. Entry to the draft tube. Okay, and if this is section 2 for example, then normally, you know, the head delivered is equal to V1 square minus V2 square by 2 plus P1 minus P2 by Rho J, neglecting potential heads and all. Okay, you know this. Then try to observe something. Here the pressure is P atm, but here directly if you leave this to atmosphere, the pressure would be P atm here. But since this tube is a diverging tube, since area along the flow increases in a draft tube, velocity, since it's incompressible, you know, this implies pressure increases. Right? Because if you apply the Bernoulli equation between these 2 points, the velocity is decreasing because of the continuity, so pressure would increase, which tells you that when this fluid is at this point, the maximum, if you leave it to atmosphere, the maximum pressure of P2 is 1 atmosphere. Okay, but now after traveling all this distance, after increasing the pressure here, so here P2 is 1 atm, right? So this implies P1 is less than 1 atm, right? In this case, so don't get confused between these two, P1 and P2. Here the terminology is like, okay, let's call this to be 0.3, and let's call this to be P3 for example, and this is state 2, let's say exit of the turbine. Okay, because so that the both nomenclatures will match then. So this is section 2 and this is section 3. So P3 is actually 1 atm, which tells you that P2 is less than 1 atm. Okay, so if P2 is less than 1 atm, that means with the help of a draft tube, if the pressure difference across the turbine is high, the head developed would be high. Okay, so this quantity should be high, then ultimately this will also be high. Correct? So with the help of the draft tube, what you're doing, you're actually decreasing this P2 much below the possible value. Okay, so if P2 is decreased below the available value, then ultimately because of that there is an advantage for the turbine and the turbine can generate more work. Got it? Did you understand? How does a draft tube help actually? Yeah, type in the chat box. Initially we would have gone only up to 1 atmosphere pressure, but now because of this draft tube, you can go to the pressure which is less than 1 atmosphere up to the exit of the turbine, so that because of the increase in the pressure difference, this head delivered to the Francis Turner is high by increasing velocity at the exit of the turbine. Yeah, of course. Okay, the contribution of the draft tube is because to reduce the pressure, and the pressure difference energy is supplied to the rotor again. Okay, that's why. And we have also something called efficiency of the draft tube, which is like ultimately from here to here there is an increase in the pressure, so change in kinetic energy to pressure energy by energy available at inlet, available at draft tube inlet, draft tube inlet. Okay, so this is not potential energy, please don't misunderstand, it's like the pressure energy. Okay, so pressure energy, by energy available, because obviously draft tube cannot convert 100% kinetic energy available here to pressure by the time it comes here, but it can convert to some extent. So therefore we have the efficiency of the draft tube, means how effective draft tube is converting this low pressure in creating this low pressure is what the efficiency of the draft tube actually. Okay, so you can apply Bernoulli's equation with friction loss, all these things, again the same thing. So basically this specific speed of this, I think I have given already in the beginning, so no issue, then no need to give once again. So this NST here somewhere I would have given, yeah, here. Okay, so these 3 points are also important actually here. So okay, and this mathematical analysis is also good. So the only thing is this VR1 and VR2 are equal, of course. Okay, if there is no friction along the blade, if you don't assume any friction along the blade, so for no friction along the blade, I'll write here, VR1 is equal to VR2, so that you can relate this triangle to this triangle depending on trigonometry again. Okay, so this is the basic idea that we can have. Okay, so we'll stop here for today. I think I have taught you so much. There's couple and turbine and pumps will start in the next lecture. So pumps again, we'll see some nice points again. So I hope you have understood in applying this Euler's equation to different machines like Pelton wheel, Kaplan turbine, all these things. Okay, the velocity triangle part is purely a mathematical simple trigonometry which we deal. Okay, but the idea is simple. Okay, not very complicated. Fine. So maybe I'll give you a homework question for next time. This we have already solved. Okay. So in today's class we have looked at degree of reaction, then we have seen the dimensional analysis, we have picked up some nice numbers which are like of the form p by rho n cube d power 5, q by n d cube, these are the 5 dimensionless numbers which are very effective for any turbo machine. And then we have looked at the concept of specific speed a bit. Then we have seen Pelton wheel and Francis wheel. So these are the things we have seen. Sorry, Francis runner or Francis turbine. Okay, so these are the things which we have seen in today's class. So we'll go for pumps in much detail in the next class. Basically pump is like the same formulas and all, but just like a reverse operation, that's it, where we supply the mechanical input and the fluid gains energy, that's it. Okay, calculations and all, everything will remain same, only some terminology like cavitation, net positive suction head, these things will come up. But the see, in first two classes and in today's class, whatever the half of the part I have done, this is the basic for any turbo machine, like the gas turbine, steam turbine, you have any turbo machine, it's the common idea. Okay, but we'll actually depending on the type of the fluid, type of the machine, the assumptions and the applications change, that's all. Okay, the rest of the parts are easy, no issue. Okay, so thank you all, then we'll meet on next Sunday. Yeah, because the weekdays are already packed with the timetable. Also I have some applied thermodynamics classes to teach, so we'll meet on next Sunday. Okay, yeah, thank you all, take care, bye.